Good morning, one and all. Suraj,
Yes.
it's over to you.
Good morning, everyone. I am Suraj Singh, Assistant Professor, Department of Statistics, KC College. It is my great honor today to introduce such an eminent personality, Dr. Suresh Kumar Sharma sir. Sir, currently, sir is a professor in Department of Statistics, Punjab University, Chandigarh. Sir has an teaching experience of 26 years. Sir was an ex-coordinator for systems, biology, and bioinformatics. Sir has undertaken different projects under his name. Some of his projects are public health and pollution control in Asia in collaboration with Health Effect Institute, Boston, US. Personalization of youth work in collaboration with Commonwealth Secretariat, UK. Sir has also worked with WHO and ICMR on projects related to national health profile and also on various other topics. Sir has published more than 125 research papers in national and international journals. Sir has attended and delivered talks in more than 35 international conferences abroad and delivered more than 550 invited talks in India. Sir has conducted many workshops on SPSS, Minitab, R, Stats Graphica, Statistica, comprehensive meta-analysis, and structured equation modeling. Sir has written various chapters in national and international books. Also, Sir is a global personality. For all these achievements, Sir has received various awards and honors, such as Best Research Award in 2003, Medical Research Ames Delhi, Jacob Wolfowitz Award in 2003, US, SS Gore Award in 2010, which is Best Paper in Environmental Health, Shiksha Ratan Award in 2011, Best Citizen Award in 2012. Also, Sir was appointed as advisory board member in London School of Management Education. Sir was appointed as chief statistician in Global Harmony Project Sweden and Russia. Sir has received Anil Malhotra Award for Best Paper in Drug Addiction Psychiatry. Conference held at PGI Rohtak, Haryana in 2018. Recently also, Sir has received Excellence in Research in Biostatistics Award by Venus International Science and Technology Award 2020. Along with all these great achievements, Sir has guided several students, out of which 12 students has completed their PhD and 4 are enrolled at present. 4 students completed their project in the area of bioinformatics. 4 PGMI doctors completed their MS degree. 1 doctor has completed DM and 3 bioinformatics students have completed their PhD thesis. Also, Sir has guided 6 MPhil students. So, Sir, we are really looking forward to this workshop as it is a wonderful opportunity for me as well as for all my colleagues and definitely for all the participants present here to learn from your great experience. Thank you, sir.
So, thank you, Suraj Singh. Now we'll start with the meta-analysis, and many people, they have the knowledge of statistical test right from the beginning. They know descriptive statistics, they know t-test, ANOVA, analysis of variance, one-way, two-way, repeated ANOVA. Then also, if the assumptions of normality, independence, etc., they are not satisfied by your data, then we go to non-parametric test, and there are parallel tests in non-parametric if your data doesn't satisfy the set of assumptions. So all this we have learned actually. Then analysis of covariance, then MANOVA, multivariate analysis of variance. And if you look at the another multivariate techniques like cluster analysis, factor analysis, discriminant analysis, all these techniques we learn in regular course of MSc, MPhil, or sometimes during the pre-PhD program. But as far as meta-analysis is concerned, many people are not very aware of meta-analysis because it is analysis of analysis actually. And how to combine different type of studies, that is the problem of meta-analysis. And there are a lot of challenges while doing meta-analysis because many studies, they report different things. Let's say one study is there which can give results in terms of risk ratio. Another study can give results in terms of, say, odds ratio. And there could be another study which is simply specifying the numbers, number of events and the total number. And there could be some studies which are having mean and SDs. The question is how to combine all these studies together. That is a challenge and a big challenge. And answer to this is given by what is called meta-analysis. Now, meta-analysis is used in many problem-solving aspects. For example, in medical sciences particularly, it is used because people are conducting different studies in different areas. They are looking at for example, let's say one of the diseases is called AMD, age-related macular degeneration. And there are standard medicines available for that for that disease, and that is called Avastin. So people give Avastin for AMD. And now it is given in the entire world. People are conducting the studies, what is the effect of Avastin in their particular sample size if they take and then study, let's say in Sweden, Russia, in India, in US. So they have different kind of samples from. The question is how to combine all of them. And can we say that at the global level, this Avastin is effective or not? So that is the idea behind meta-analysis. Similarly, people are using index numbers. Let's say in India, we compute index numbers based on Lespier's index, Pasteur's index, Edward Marshall. There are so many index numbers. And in many countries, they are computed in different ways. In some countries, they are using Lespier's formula. In some countries, they are using Edward Marshall formula. In some countries, they are using Pasteur's formula. But index number is there for all. The question is how to combine all of them. So this is another problem of meta-analysis. Similarly, people compute birth rate for different countries. There is a crude birth rate, there is a standardized death rates, and each and every country, they are using different formulas for death rates. Next question is how to combine all of them together to come out what is the death rate of the entire globe, of the entire world. Similarly, you can talk about the entire birth rate of the world. So all these challenges are being faced in meta-analysis. It's not an easy task. You have to look for so many factors because of the studies are not homogeneous. Many studies are going to be heterogeneous. And there are many statistical tests through which you will be able to identify whether the studies are homogeneous or they are heterogeneous. So we have to go through all these in meta-analysis. So in first 1.5 hours up to 12 o'clock, I will be discussing about, now it is just 1 hour, 15 minutes, the theoretical aspects of meta-analysis. What do you mean by fixed effect? What do you mean by the random effect? What do you mean by the mixed effect models, right? So all these things will be discussed right in the first part. And after that, in the second part, I'll go for a practical demonstration using R. Of course, there are many statistical packages through which meta-analysis can be analyzed. And one of the important package in meta-analysis is called CMA. CMA is called Comprehensive Meta-Analysis. This is such a great package. And Borenstein, the main person who has designed the CMA, Comprehensive Meta-Analysis, and many other authors are also there. They have designed in such a way that even if you have some studies, they are reporting risk ratio, some studies reporting odds ratio, some studies reporting mean and SDs, some studies reporting proportions. You can bring them, all of them, to one platform, and all of them can be converted into a single factor, and that is called the effect size. And effect size is generally measured through risk ratio or odds ratio. So, but these flexibilities are not there in other packages. For example, if we want to do meta-analysis in R, then we have to be very clear whether we are dealing with the correlation data or we are dealing with the mean and standard deviation data, then all these, they should have the similar format. But in comprehensive meta-analysis, because I downloaded that package for a period of 15, 20 days, it was a trial version. After that, you cannot access that. But I have seen the applicability at large, and you can, if any institute can afford comprehensive meta-analysis, it will be a great boost to that institute, because this can cover a wide variety of problems relating to meta-analysis. Okay, so let me share the screen and start with the presentation. Can you see my desktop?
Yes, sir.
Okay. So I have given you some idea about meta-analysis. Now I will be referring some technical terms. And if you understand these technical terms, then it will be very easy. For example, in MOS also, there are many technical terms. And if you understand the technical terms, then the things becomes easy. For example, in meta-analysis, what is a systematic literature review? Then it is different from literature review. Then also the terms like meta-analysis, what is the meaning of the different tests like Q statistics or I-square statistics or tau-square statistics, then where to use the weights, which kind of weights are there. So all these we require before conducting the meta-analysis on any set of studies. Okay, let me start with. So I'll be covering the basics of meta-analysis using fixed, random, and mixed effect models. So first of all, I would like to thank Dr. Harsha Bagle, the principal of the college, and now it has become HSNC University in Mumbai. And they are conducting many workshops in R, in MOS. Last time, I think I conducted a 3 days workshop on MOS for KC College. And the videos are available. If anybody is interested, they can approach madam also. And the access, even in fact, YouTube videos are also available now. Okay. This is our Punjab University, Chandigarh, from where we are, Professor Kanchan Jain and myself. She is my teacher, as I mentioned. And we have learned a lot of things from Professor Kanchan Jain. And she is expert in reliability theory and many other areas. And we have a department of statistics, very active department of statistics. It comes at number 2 after Pune in the entire country. Okay, so this is 550 acres of land, and with 89 departments and many other centers, more than 180 affiliated colleges. So huge university established way back in 1882 at Lahore, and shifted after partition to Chandigarh. And you see, it has more than 22,000 students, excluding students, those who are in USOL, University School of Open Learning. And all together, if you combine all the student strength, it is more than 4 lakh, because there are colleges also there. Okay. Let me go through what are the books which one can follow, or the study material you have to look for. There is an important book that refers to the basics of meta-analysis by Borenstein, Michael Borenstein and Hedges. It's a very important book, but this covers all the basics which are required for meta-analysis by Wiley publication, and the title is Introduction to Meta-Analysis. And if you look at the simple funnel plot or radial plot or other kind of plots, they're all discussed here, and the entire applications are also given, but not discussed in much details. If you are looking for the publication bias or bias in research findings, then you have to go through this second book, Methods of Meta-Analysis by Hunter and Smith. So it is also a very important book, but this is some advanced level book. But for learners, if you start from Michael Borenstein's and Hedges book, it will be beneficial to you. After that, once you read this book, then you can come to Methods of Meta-Analysis by Hunter. And there is a third approach now, third approach of meta-analysis by using structure equation modeling approach. And this is again a Wiley publication by Cheong Michael W.L. Cheung. And I haven't gone through this book. I have gone through these two books. This is some advanced level and this is basic level book. So this is the study material for any MSc or those students who want to pursue their research in the area of meta-analysis. Okay. So what is meta-analysis? As I mentioned that it is analysis of analysis. I have given you several examples of meta-analysis. Basically, an objective and quantitative methodology for synthesizing previous studies and research on a particular topic into an overall finding. As I mentioned, that you have to find out the overall, what is the conclusion of all these studies together. So meta-analysis allows us to collect, code, compare, and combine results from different studies and interpret using statistical methods, facilitating statistical guided decisions about the strength of observed effects and the reliability of the results across a large range of studies. For this purpose, we use what is called meta-analysis. Now, there are two important aspects. People get confused with systematic literature review and meta-analysis. Basically, meta-analysis is a sub-part of systematic literature review. Basically, you can think that it is just a subset. Meta-analysis is a subset of systematic literature review. In systematic literature review, you are just collecting the information wherever it is available. It could be available in unpublished papers. It could be available in some books which are not very well known, or it could be published in different languages. Sometimes we say that I have gone through all the research papers relating to this topic. But question is whether you have gone through the research paper which have been written in French, whether you have gone through the research papers which have written in German. That is not possible for anybody. So systematic literature review is basically an umbrella where it involves three steps for systematic literature review. First step is called planning stage. And in planning stage, what we required is you identify your problem and then look at the review team. For example, when we were doing a research on thyroid cancer with Professor Raghava from IMTech, we have a proper team. We selected a team that these are the people who can work together and put over, and we come out with the website then, which is called Cancer PDF. So selection of the team, because those people who are involved, they have to be very much familiar with the topic of the research. Then exploring the relevant literature. Then you have to explore the relevant literature. That is called the planning stage. And then next stage is what is called conducting stage. Then you have to, as I mentioned, search term. It's a broad topic in itself. It has to be criteria wise. As I mentioned, that there could be literature which is in different languages and may not be directly available to you, but systematic literature review may include all of such type of literature also. Then you have to fix in right from the beginning the inclusion and exclusion criteria for your study. Then after you fix your inclusion and exclusion criteria, then the review team which you have, they have to assess again, and they have to sit together. They have to put their brains together, whether we are moving into the right direction or not. Then final list of studies which you want to include into the meta-analysis, that has to be selected. And obviously after that, you have to go for the analysis using meta-analysis technique. So that is what is called the stage number 2. And then in stage number 3, we have to look at the present findings. What are the main objectives, whether you are able to achieve them or not, recommendations for the future research. So all these things we required in the reporting stage. So I'll give you some other aspects of systematic literature review. So how to do meta-analysis? The first part is to go through the entire literature research, which is called the systematic literature review. Then they compile the results of these studies in a proper format. And most of the times, the proper format, either let's say we are conducting studies based on mean, SD, and number, then you should have that kind of format. If it is simply referring to the events and the total in experimental group and the control group, then you can have another format. Your format could also be based on let's say 2 by 2 table contingency tables, where you compute generally the risk ratio or the odds ratio. So you have to define, I'll discuss about the different kind of formats which are available. And then all these statistics, whether it is relating to mean SD, whether it is relating to odds ratio, whether it is relating to risk ratio, all they are converted into what is called the effect size. If you are dealing with the mean and SD, the effect size will be your mean difference. If you are constructing the, let's say 2 by 2 kind of table, 2 by 2 contingency table, then your effect size may be in terms of risk ratio or odds ratio. So depending upon the problem, we have to look into the effect size and convert all the statistics to the effect size. Effect size basically in meta-analysis is called the heart of the meta-analysis. Everything is being converted to effect size. Then meta-analysis is not easy to do with hand. You need a software, and there are many softwares. I'll be mentioning few of them. And these softwares are, some of them are free software, some of them are paid software. In free softwares, if you look at R&R Studio, they are free softwares. Then one of the software which is also free is called Review Manager. So you can download that, and in Review Manager also you can do meta analysis. But the restriction in Review Manager is that you can do meta analysis but not meta regression. You cannot do meta regression there, right? And then there is another software which is called Jamovie, and Jamovie is also a free software in which you can perform meta analysis. So like this, there are add-ons to Excel also. There are add-ons to Excel, two add-ons to Excel, and you can also use them for meta-analysis. Now, let me tell you, there is one university in Netherlands that is called University of Rotterdam. And University of Rotterdam has a free software which is called Meta Essentials. And you can download that and you can work on that. It's a free software, but there are some limited options. There are 5-6 options. If you are having mean SD, risk ratio, odds ratio, proportion, etc., all these things can be handled by using this Meta Essentials, and it is freely available. And you just have to feed your data and you will get the result. And just click on to funnel plot or forest plot, everything will be available to you. So all these packages are there which can help us to do meta-analysis. Then finally, we have to report the results of the meta-analysis. Okay, so difference between systematic review and meta-analysis. As I mentioned, meta-analysis is a subset of systematic review. You look into the broader literature, then you try to concise this into manageable form, and finally you pinpoint that these are the studies which we need for meta-analysis. So a systematic review attempts to gather all available empirical research by using clearly defined systematic methods to obtain answer to a specific questions. And meta-analysis is a statistical process. You see, in systematic review, there is no statistical process involved. That is the main difference between systematic review and meta-analysis. It is just basically a collection of the literature, right? While meta-analysis involved a statistical process of analyzing and combining results from several similar studies. So another, some key points in the difference between the systematic review and meta-analysis: identify and critique relevant research studies, discuss factors that may explain heterogeneity, synthesize the knowledge, and in meta-analysis, identify relevant research studies using a defined protocol. Statistical tests study heterogeneity and investigate explanatory variables, and statistically summarize results to obtain an overall estimate of the treatment effect. Okay, so these are the different kind of sample formats which people use in meta-analysis. For example, your studies, I've just named arbitrarily A, B, C, D, D, E, F. These are the studies conducted in different years. And these involved, let's say, this first study is based on 40 observations, and they have given the correlation as 0.5. Similarly, the another study is based on 90 observations. They have given the correlation as 0.6. Similarly, others. If you see, there are studies which are having some large samples, there are small samples. The question is how to combine all of them together. And another problem you can always see that some of the correlations are positive and some of the correlations are negative also here. Why? Then you have to be very, very clear why these two studies, they are having negative correlation, why they are having positive correlation. Is there any special thing which is behind all these studies? Or then you have to be, maybe you have to perform the subgroup wise meta-analysis. You can separate out those studies which are having negative correlation, and you can separate out those studies which are having positive correlation, and separately try to go for the meta-analysis. That is called subgroup meta-analysis. So that is one of the format where correlations are available. Another sample format may be, let's say you have two groups, or let's say experimental and control groups. Then these are the study years again, and then you have number of total number in the first study, total number in the second study, and let's say x1, how many people are there, how many events have occurred, let's say in experimental group, how many events have occurred in control groups. Sorry, this is concerning with mean and SD numbers, and let's say x1 denotes the mean of the first group, let's say experimental group. Then this is the mean of the control group. This is standard deviation of the experimental group, standard deviation of the control group. So your format may be in terms of mean, SD, and numbers. Your format may be in terms of correlation. Similarly, there could be other formats like odds ratio, like risk ratio. As I mentioned, that comprehensive meta-analysis is such an important package that if you have the data in any kind of format, whether you have in terms of correlation or mean SDs or odds ratio, risk ratio, you can put all the data into one file, and it will give you the effect size. Okay. Now, these are some of the prior things which you should know before conducting the meta-analysis, because you need to interpret the results. What do you mean by the p-value? Generally, people know that if p-value is less than 0.05, then the result is significant. Otherwise, it is non-significant. Yes, even if you know this thing, fine. Confidence limits or the confidence intervals. Confidence intervals may be for difference of means. It could be for correlation. It could be for risk ratio, odds ratio. So one should be very clear about confidence limits. For example, if I'm saying, say, 95% confidence limits, that means if you conduct 100 such parallel studies, at least, let's say, mean of 95 studies will come out within these limits. Then power of the test is also equally important, because there may be studies which are having very less sample size and power may differ. So power of the studies basically is directly related to the sample size. Of course, it is related to many other aspects also. Then concept of univariate analysis. It's not necessary that meta-analysis is performed on bivariate or multivariate only. You can perform meta-analysis for univariate also. For bivariate analysis, for multivariate analysis, these techniques, if you know, it's fine. Otherwise, I'll discuss today a little bit about this thing. Then basic understanding of the center tendency and variation measures, then understanding of the t-test, ANOVA, correlation, partial correlation, regression, and if we will not discuss about structure equation modeling, that is the last part. Okay. Now, let me give you a very simple example that how generally we get the results out of the meta-analysis. Suppose this is input from the systematic literature review, and you able to finalize few studies. There are 5 studies here, and these are the correlations you have computed based on the different sample sizes, right? Now, out of this, generally meta-analysis, if you perform meta-analysis, a forest plot will be given to you. You will get a forest plot, and forest plot is basically depicts many aspects of the meta-analysis. For example, let's look at the first study. Its correlation is 0.2, so you can see a centered one dot there at 0.2. Similarly, look at the second study where the correlation is 0.5, so you can see a one single dot at 0.5 there, right? I'm just giving you a hypothetical example. What do you mean by forest plot? Then 0.4, the next study, number 3. So 0.4, third, this is 0.4, right? Then you have 0.1, that is here, and then 0.35, that is here. So I have marked all these studies. Now you can see there is a circle, and this circle or the dot point, they varies in size. Now, what is this size actually? It depends upon the number of observations. For example, look at the fourth. This is having a bigger circle or center. The reason is because it is based on 400 observations. So that's why it is capturing the fact that it is based on the larger number of the sample size, larger sample size. Similarly, look at this one. This is based on just 60. This is based on 250, slightly smaller than this one. So this size basically depict the size of your sample. So you can interpret like that. And moreover, there is a line. You can see this is the line. This is the line. This is also a line. This line basically denotes the confidence intervals. Those who are from statistics, they know how to get the confidence intervals for R. Generally, we use Fisher's-Jack transformation. And in Fisher's-Jack transformation, we get the confidence intervals for R. And you can get the confidence intervals for R. These are basically 95% confidence intervals around this point, which is 0.2. Similarly, for all other studies, we have computed the confidence intervals. So there are 5 studies. So there is a middle point which denotes your outcome. Basically, outcome is your correlation. And in outcome round, you have the confidence intervals, and confidence intervals, the circle depends upon the size. So all this is being interpreted by what is called forest plot. Now, what is this line then? There is a black line here and there is a circle also here. This denotes the what is the overall if you combine. The question is, can I take the average of all this? Can I take the average of all this? No, answer is no. Not in meta-analysis like this. You cannot take average of all the R's together and put it here. That's not the right thing to do, because the reason is very simple. Some studies are having larger samples, some are having smaller samples. You cannot combine them together by taking a simple average. So here what we require is what is called the weighted average basic. Of course, it is an average, but it is in terms of the weighted average. And when you compute, I will come to the weights, how to assign weights using fixed effect model, random effect model. So all these things will be discussed. And this is the overall conclusion. So if you see the overall conclusion of if you combine all the 5 studies together, this will be the point, and this will be the confidence interval. This will be the confidence interval for if you combined all these studies together. So this is the outcome of meta-analysis when you combined all these studies together. Now, one important point in forest plot is if this line, any confidence line is crossing this line is basically called line of no effect. This line is called line of no effect. And if your confidence intervals crossing this limit, for example, study number 1 and study number 4, they are crossing this line. So that means these studies may have some problems. So at the class, you can look at that wherever there are certain problems are there, and you can also see these correlations are very, very low. It is 0.2 and 0.1. So these type of studies may have certain problems if they are crossing the line. So that is the interpretation of the entire forest plot. I will discuss about the forest plot while giving you the practical demonstration also. So this forest plot is based on simply a correlation and its confidence intervals. Similarly, your forest plot may be based on odds ratio. It could be based on the risk ratio. It could be based on the mean difference, depending upon the research problems or the research studies which you have gathered for the meta-analysis. Okay, this is the output. If you look at, so here we have the study weights. Study weights depend upon your sample size, right? This is the confidence interval, as I mentioned, and this is called the summary effect. This is called the summary effect. Now, summary effect varies from summary measure to measure. Measure means this is called basically summary measure. Your summary measure may be in terms of odds ratio. Your summary measure may be in terms of risk ratio. Your summary measure may be in terms of mean difference, right? So, but summary effect, the overall conclusion is called summary effect. And then you have the confidence intervals. And these are the study weights. Hopefully, each and everything is clear from. And this is called the line of no effect. And what is this green line? Green line is basically denoting your prediction intervals. And remember, for any study, if you compute, your prediction intervals are always going to be larger than the confidence intervals. Prediction intervals are always going to be larger than the confidence intervals. Remember this thing. And if you want to see the proof of this, you can go through a book by Bowerman and O'Connell, where all the prediction intervals formulas are given. You can compute the prediction intervals yourself. Okay. Now, concept of heterogeneity and homogeneity is very, very important in meta-analysis, concept of heterogeneity and homogeneity. Now, what does this mean? Look at, I have defined here two types of studies. One study is here, and these are their correlations. One study is here, these are their correlations, right? Now, if you plot the same way, let's say I'm simply plotting the correlation values, and this denotes the sample size and then their confidence intervals. And you can see that all are positive here in the first one. In the first one, all are positive here. So it seems to be that they are referring to some kind of homogeneity. Just a rough idea about homogeneity, that there may be some kind of homogeneity, and homogeneity also refers to the closeness actually. And if you see the correlations, it is 0.5, 0.35, 0.48, not very far away. Of course, 0.6 and 0.35 there, that is one, but still not. They are on the positive side itself. So you can think of that more or less they are homogeneous in nature. But look at this one, which I have also plotted previously. This is, if I take this as 0, there are 3 studies with positive correlation and there are 2 studies with negative correlation, right? Now, you can think of, can I combine them together or not? It's a big question. It's a big question. Maybe in such type of situation, you require subgroup meta-analysis rather than going for the overall meta-analysis. And that is what do you call heterogeneity. So in this type, the heterogeneity may be present. Here the homogeneity looking to be there, that these studies are more or less homogeneous in nature and these are heterogeneous in nature. That is a rough idea of the concept of homogeneity and heterogeneity, but we will discuss about the test of homogeneity and heterogeneity largely when we'll go through the practical demo. Now, there are 2 types of models which are generally used in meta-analysis. One of them is called a fixed effect and another is called the random effect. And people get confused where to use fixed effect, where to use random effect. Let me tell you, I have gone through a lot of literature of the meta-analysis. Let me tell you, a rule of the thumb is in 90 to 95% of the cases, people use random effect. Because there is a restriction with fixed effect. Restriction of the fixed effect is that all the studies, they should have the common effect size. And that is not hardly achieved in most of the studies. Very difficult to achieve that they should have the common effect size. I'll give you examples of fixed and random effect just after this slide. So just look at the definition. Here we assume that there is one true effect size, one common single effect size. That means all the studies which you have included, they are converging to one, right? And that is a true effect size, which underline all the studies in analysis, and all the differences in observed effects are due to the sampling errors. It's not due to any error. It just involves the sampling error, which is just beyond your control. And in fixed effect, you cannot generalize your results. Let me just repeat. In fixed effect, if you're using fixed effect, you cannot generalize your results. But in random effect, you have a lot of flexibilities. Because here we allow that the true effect could vary from study to study. And generally it happens in practical situations. And if it were possible to perform an infinite number of studies, then the true effect sizes for the studies would be distributed about the mean, right? And purpose is basically to generalize the results. That we have conducted 15 such different studies. If people also study, they will get almost the same conclusion because we have generalized the results. So random effects is used in 90 to 95% of the cases. Only in 5% where you are 100% sure about something, that all these studies are very, very close. They have been taken under the same environment and all these things. Then and only then we use fixed effect size model. Okay. So here is an example of fixed versus random effect statistical models. So this is the fixed effect. Fixed effect means, let's say I'm looking into, say, Chandigarh or maybe Mumbai, or Chandigarh is a very small place with a population of around 10 lakh people. And there are government schools actually. In each and every sector, we have a government school, government models, senior secondary schools, right? And if you overall look at the performance of all these schools, in government schools, I am saying, only on government schools. And if you look at their average how many students they pass, it is between 80 to 85%, sometimes between 80 to 90%, right? If you look at the all the statistics of the government schools in Chandigarh. So, I mean, if I'm just focusing on the government schools, I can think of applying fixed effect size because they are referring to government schools more or less. There are students from all types of backgrounds and their average score may converge to some number. That is called the fixed effect size. But let's say in Chandigarh, there are very good schools also. There are government schools also. There are convent schools. There are some high profile schools also, right? And if I'm conducting the study that what should be the overall performance of all the schools of Chandigarh, then obviously I cannot go for the fixed effect. I have to go for the random effects because I know even if you are, let's say, looking at the English language, obviously those who are convent school people, their score on English are going to be high as compared to those who are in the government schools. There, you know the reasons for all them. So I have to go for random effects rather than the fixed effect size. So you have to be very clear. As I mentioned, most of the time we are using random effect models. Okay. Now, fixed versus random effect again. Generally, it is dealing with one population. As I mentioned, the one population means government schools only. While this is involving the universe of populations, maybe convent school, maybe some high-profile schools, and so on. Right now, if you are dealing with the fixed effect size, your weight depends upon how many observations and which study is having the largest number of observations. For example, here, if you compare these 4 studies and this is the 5th one, let's say, its size is almost 5 times. So it has to be given more weightage because it's based on sample size. So if you are using fixed effect size, it is based on your sample size. So here you are assigning more weight. But if you are using a random effect model, the weights are more or less evenly distributed. Sometimes, depending upon the type of study, it may be double, but generally not more than 3 times. And the weights are going to be like this. Here, weights are going to be like this. So hopefully understood that in case of the random effects, weights are more or less evenly distributed, while in case of the fixed effect size, the weights vary from depending upon the size of the sample. So you have to be very, very clear. That's why I'm saying in 90 to 95% of the cases, people used random effect rather than fixed effect. Because if you look at the previous study, let's say look at this one. This is involving a sample of size 400. And if you look at the total sample size, maybe it may come out to be 750 or 8 something. Out of that, 400 is belonging to this only. So 50% or the more than 50% weightage is going to only this study. So it will be given a weight accordingly. So you have to be very, very precise while dealing with the fixed effect size. Okay. So this we discussed. Now fixed versus random effect. If you are dealing with multiple populations, you cannot go for the fixed effect. You have to go for the random effects. Generalize to similar populations. You have to go for random effect. Assess heterogeneity, then again random effect. So generally fixed effect is not used in such kind of situations. Now decision about the weights, very important because there are 2 different formulas of weights. Generally weight is taken as one of the inverse of the variance, right? That is generally in many studies, this is considered as a weight. But if you are using fixed effect, it is simply 1 over variance. Then you can consider that as weight. But in random effect, there is additional component and that is called W is equal to 1 over the variance plus tau square. This tau square, there are methods to estimate this tau square, and this tau square refers to between study variation. This tau square this is within study, this is between study variation, right? So weights are computed in different ways if you are using random effects. But if you put tau square equal to 0, then they will coincide with each other. Your random effects will be same as the fixed effect model. And I'll give you examples. If tau square will come out to be 0, then that your overall estimates, they are marginally differ from each other. You will get almost the similar sets. Okay. Now, as I mentioned, there are terms in meta-analysis. This we have already discussed. Generally, systematic review is related to qualitative summary and meta-analysis is related to quantitative quantitative summary. And here we use statistical techniques. There is no statistical techniques in systematic review. Now, here is another important picture to look into, that one of the views in literature is called traditional narrative reviews, which include different studies from different languages. So it's a broader circle. It's a broader circle, right? Then your filtering process goes on, and you come to systematic reviews. You, based on your study, what you require, then this is a filtering process. You have come out that these are the studies which may be important, which are not important for my study, which may be important. So it's a bigger circle. And then looking at some statistical techniques, sampling techniques, you further try to concise this. No, this study is beyond, this is beyond. And then we go for the exact studies to be included into the meta-analysis, right? And this is the inner circle. So basically, as I mentioned, that meta-analysis is a subset of basically systematic review. It's a subset of systematic review. Now, these are the steps involved in meta-analysis. First problem is to formulate the research question. Your study is about which kind of problem. It may be that you are looking into certain problems relating to heart disease, and people are giving different medicines for heart disease, right? And you are looking at the effect of this medicine on control group, on experimental group. So formulate the research problem accordingly. Then set of inclusion and exclusion criteria have to be mentioned very clearly. Then identify studies which satisfy your inclusion criteria. Develop a coding protocol, proper coding protocol, because you are going to generalize the results. You have to give the proper protocol of your meta-analysis. Then code different studies like 1, 2, 3, 4. You can code ABCD. You can code. Then select the effect size and precision. And there are many methods of precision I will discuss in subsequent slides. Then convert into effect sizes. Then determine the effect size model, whether we have to apply the fixed effect or the random effect, or sometimes the mixed effect model. Compute heterogeneity statistics like Q statistics, like Tosca statistics, like I-square statistics. They are measures of heterogeneity. Determine population bias. So there is a funnel plot for population bias, and you can go through the funnel plot to see whether there is a publication bias or not. And it can identify whether there is a publication bias. Publication bias generally occurs whenever you are conducting some meta-analysis and you have left out certain studies which you haven't come across. They may be unpublished, they may be in different languages. Then this problem of publication bias is there. And finally, the interpretation of the results. So between study variance methods, I have not gone into each and every method into much details, but the most common method used for estimators, how to estimate the variances of the different studies, that is based on, even R is using a metaphor, and in metaphor they are using this method which is called REML, which is called restricted maximum likelihood. So this is a default method used in metaphor. Of course, there are many other methods like D. Savanian, Lloyd's method, Hedges method, Hunter method. All these people are well known in the area of meta-analysis. I have the book. More than they are Hedges and Hunter. They have written a book on books on meta-analysis, right? But we will be using this thing only, which is called the restricted maximum likelihood estimate. Okay, then measure of heterogeneity. How to measure heterogeneity? There are two important statistics. One is given by Hedges, and that is called Q. This sometimes is also called Cochrane Q. And another is given in terms of the percentage. And most commonly used heterogeneity measure is in terms of I-square. And I-square give you the results in terms of percentage. And if it is between 0 to 30%, then you should not bother about heterogeneity. Heterogeneity is very, very low. Moderate type of heterogeneity will arise if it is between 30 to 60%, and substantial if it is more than 60%. So generally, I-square is considered by most people because it is easy to interpret. Of course, I-square doesn't give you a p-value, but Q will also give you a p-value. So there are two important heterogeneity measures in statistics, and which when you perform meta-analysis, you will get two different types of statistics. One will be based on Q, another will be based on I-square. Okay, but Q will give you p-value. I-square will not give you p-value. It will be in terms of percentage. Okay, then publication bias, as I mentioned, that whenever you are conducting studies, some studies may be there which you have left out, and to test whether is there any study which we have left out, then we can go for further analysis, and that is called publication bias. And testing for publication bias, there are 2-3 important procedures. One of the important procedure is called funnel plot. I will show you now what is the interpretation of funnel plot, and then I'll move forward. Funnel plot is such a plot that in the center there will be a zero line. On the left and right side, your studies will be distributed equally. They should be distributed equally, and if they are not distributed equally, then you can assume that there is a publication bias. And how to identify publication bias? There is a method, and that is called trim and fill procedure. Trim and fill procedure. And let's say you are conducting 13 different studies, and in funnel plot there is a publication bias. Then you want to see how many studies I have left over, maybe 3 studies, 4 studies. So once you go for trim and fill procedure, it will give you that you have left out 4 studies, you have left out 5 studies. I'll show you this, how this thing will happen, right? So that is covered under what is called the publication bias. There are, as I mentioned, measures of heterogeneity in terms of statistics. One of them is called, as I mentioned, Q statistics, which is called Cochran's Q, and this is the interpretation. It is only a measure of variation around the average. Actually not measuring the heterogeneity exactly, but it is just around the average. Then I-square, which is generally used, a percentage is between 0 to 100, and it is nothing but proportion of the observed variance that reflects the real differences in effect size. Real differences in effect size, that is given by I-square. Then this is tau-square. Tau-square is estimate of the variance of the true effect sizes used to assign weights to the studies assuming random effects. Please remember, this tau-square is used only for random effect model. Then if you take the under root of tau, then this is give you the standard error, or sometimes called standard deviation. Estimate of standard error is called standard error, right? And this help you to find out the prediction intervals. This help you to find out the prediction intervals and confidence intervals also. Okay, so these are the important 3 measures of heterogeneity in terms of statistics. Q statistics, it will give you a p-value. I-square statistics, it will give you just a percentage. And tau-square statistics, if tau-square statistics is coming out to be 0, let's say tau-square is coming out to be 0, then whether you apply fixed effect, whether you apply random dimension, you will get the same results. Okay. These are their formulas to compute. Those who are interested into statistics, this is the formula for Q, this is the formula for tau-square, this is the formula for C, and this is the formula for I-square, right? Depending upon which type of studies we are conducting. For example, if you're dealing with experimental and control, obviously you want to compare with the help of T statistics, so degrees of freedom of T statistics will be used. Similarly, if you are having some other statistics like risk ratio, odds ratio, then again there are tests for risk ratio, and you are using different kind of degrees of freedom, right? So first we compute Q, then we compute C, then we compute this tau-square, and after that finally we compute this. Okay, so these are called heterogeneity measures. And test for heterogeneity in terms of I-square is very simple. This is minimal. If the percentage is between 0 to 30, 30 to 60 is moderate, 50 to 90 is substantial. I mean, these are given in different literature. One of the literature was previously, which I have shown, it's given in another literature, but this is more being followed by the people. So 90 to 100% is considerable heterogeneity. Okay, now let me give you an idea about the forest plot and its interpretation, because we have to draw all these plots in the second session, and I'll come up with certain data sets, and we will draw all this, but try to understand the meaning now. If you look at there are few studies here which I mentioned. The studies are always mentioned on the left hand side. Then this is a prevention and some let's say experimental and control group. Then you have mean and SD in the total number. 3 things you required if you're dealing with the experimental and control group. One is the mean, another is SD, then you have the total sample size. And similarly, in control group, you have the mean, SD, and this. And these are the weights which is generally computed. I have given you a formula for weight, and it is by using the random effect model, right? Because we are using here random effect. If you use fixed effect, you can see a lot of variation here. You can see a lot of variation because it depends upon the sample size. So generally, weights are computed based on the random effect model. So then, as I mentioned, that this point refers to your standardized or the standard mean difference. Standard mean difference in the two will be 0. Then you look at the first study. First study, it is here. And how to combine the results of this study. This is basically the mean and its confidence intervals. Mean and its confidence intervals. Now, this is if you are using some intervention, then these are the studies which favors intervention. Please try to understand. These are favors prevention. I mean, favors intervention. And these are control group doesn't favor intervention basically. So out of so many studies, you can see 1, 2, 3. If it is crossing, it may not favor. So 1, 2, 3, 4. 4 studies, they are favoring your intervention. That intervention is important for you, right? So there are 3 aspects of basically the forest plot. One is called the descriptive statistics. So here is the entire descriptive statistics. Then this is called the graphical procedure, which is called the forest plot. And then we have the statistics. So there are 3 aspects, 3 basic aspects of any forest plot: the statistics, the descriptive statistics, and the forest plot. But major idea you can get from the forest plot. Now, all these studies, they have the mean and their confidence intervals, everything. And what is this diamond now? This diamond is basically combining of all the studies together. So there is, if you look at the center, then this is the confidence intervals. This is the confidence intervals, right? So all these things are captured in what is called this forest plot. Now, out of the 7 studies, I think 1, 2, 3, 3 are not favoring the intervention, and 4 are favoring the intervention. And what is the overall results? Overall results is on the left-hand side of this line, which is line of no difference. So what is your final conclusion? Final of conclusion is, yes, we can say that if some intervention is given, intervention could be any medicine, it could be any educational background, or it could be some advisory or something like that. It could be in terms of, let's say, some medicines like you are giving in AMD, you are giving Avastin. So effect of Avastin. So overall result says that the intervention is preferred in most of the studies. Overall, it is not. If you look at only 2 studies are here, actually only 1 study is on the right hand side. So this is not favoring intervention. So here clearly this is not favoring intervention, while all of them, they are favoring intervention. Of course, their confidence intervals are crossing the line, but they are favoring intervention. So if you look at out of the 7, 8 studies, 8 studies, let's say 7 are favoring. 1, 2, 3, 4, 5, 6, 7. So out of the 7, 6 are favoring the intervention. 1 is not favoring the intervention. And overall effect is that intervention is important. Intervention is important. Now look at these statistics. There is a I-square, it says I-square is 79%. As I mentioned, I-square is the most important heterogeneity measure. It is 79% means what? It is coming closer to 100. So that means there is a heterogeneity present among studies. They are not along the state. They cannot be converged to a single fixed factor type of mean. You can see means are different. They are not same. So that's why we have used the random effect model, because the heterogeneity is more. Then this square, as I mentioned, it's another variance, 23% of the variance. This is this. If this would have been 0, then fixed effect and random effect would have been the same. And it says that the overall effect, this is the overall effect, which is Z in terms of Z, 2.70. And you can say minus 2.70, and with p value of this. So it is coming out to be significant. So that is the interpretation of the entire meta-analysis of this. Similarly, if you look at in terms of the, let's say, events, There are events and the total number of events. So out of the 28, how many events had happened? 2. Out of the 100, how many events had happened? 12, and so on. So this is in the preventive group, this is in another group, and then you compute the weights. And if you compute the weights, now you can look at the risk ratios, and the interpretation is almost the same. Why I discuss about this? Because if you look at these studies, none of the studies on the right hand side, none of the studies on the right hand side. But even if you compare the overall means, if you see overall means, they are almost similar except this one, almost similar. That's why the I square is very, very low. Of course, it is given to be 0%. And most of these studies are homogeneous in nature, right? Most of these studies are homogeneous in nature. So that kind of interpretation you can have out of this. Then to look at the publication bias, we have a funnel plot. In the afternoon session, I mean, afternoon session, after 12 o'clock, I will discuss all this practically. So look at this funnel plot. This is the zero line, basically. And some studies, if they are equally distributed on the left-hand side, right-hand side, then there is no publication bias. You can immediately say there is no publication bias. But look at this kind of funnel plot. Most of the studies, they are here. And other studies are jumbled at one point, right? They are not. So this is totally a vacant while there are studies here. It's totally vacant. And it clearly, this type of funnel plot clearly shows that there is a publication bias. You must have left out certain important studies which were important for you. So that is the idea of looking at the publication bias. Okay. So up to this, if anybody is having questions, I can take up. Now I will discuss some mathematical concept before moving on to the practical session. So now the session is open. If you want to ask some questions, you can ask me. Yes, please. Anyone? If you want to ask some question, anybody want to ask some questions? Or is there any question in the chat box? Madam, you can read if there is any question in the chat box.
Sir, as of now, we don't have any questions. We'll ask participants, if you want to ask any questions, put them in chat box, or you can unmute yourself and speak.
Yes, you can please.
Okay, there is some question. Okay, so please share them. Can you explain how weights are calculated?
Yeah, weights
Actually, Sardi ma'am is asking.
Yeah, there are formulas to compute weights, and now I'll tell you how the weights are computed in this slide. Just wait for a moment. I will tell you how the weights are computed. Okay. So generally, as I mentioned, in fixed effect model, the weights are computed based on the weighted average. So it's summation WI divided by summation WI. So obviously, those studies who are having higher sample size, WIs are sample size, they will be given larger weightage as compared to the other one. But in random effect, there is a little bit complicated formula to compute weights. Yes, please. Any other question?
Okay. So, sir, another question is by Sukhamani Chahal. Is asking that how do you plot funnel plot, and what is taken on x-axis and what is taken on y-axis?
See, as I mentioned, the x-axis and y-axis. Y-axis denotes your no effect line. That means it's zero line, basically. For example, it varies from experiment to experiment. If you're talking in terms of the funnel plot for risk ratio or odds ratio, then it is given to be 1. So your center line will come at 1. Then you have the left and right? And if it is in terms of the mean difference, then your center line will be at 0. So it varies from study to study. Now, what do you mean by 1? If you are dealing with the risk ratio and odds ratio of 1, that means there is no effect of intervention. Center line denotes that there is no effect of intervention. Suppose I look at the funnel plot, and all these studies, their mean values are concentrated around the center line, That is the middle line. What is the interpretation then? The interpretation will be that there is no effect of intervention. Whether you do intervention or you don't do intervention, it is not going to affect your results. It is not going to help the patients at all. So this is what is the interpretation. If there is a risk ratio or odds ratio. Similarly, if there is a mean SD type of problem, it is in terms of the mean difference, which is center line is at 0. And if all the points are closer to 0, obviously there is no difference between experimental and control group. if their means are almost zero. So there is no effect of intervention then. Hopefully, see, one group is given placebo, another group is given some medicine, and if the differences in the means are almost zero, what is the interpretation in statistically? That means your intervention doesn't have any effect. So same thing is being captured by this plot, which is called forest plot. Hopefully, Sukhmani, this makes sense to you.
Yes, understood.
Yes,
Yes,
please.
written in the chat box.
Any other question?
Any other question, participant? You can write in the chat box.
Yes, please. Any other question? No question. Should I move forward?
I think, sir, right, they don't have questions right now. We can move ahead.
Okay. All right.
Uh,
Now let me go into the theoretical part. Actually, this part will be the first part which I have given you. That was for all the people, whether they were aware of some statistical techniques or not. That was for all the people together. So hopefully able to understand what do you mean by the forest plot, what do you mean by the funnel plot, what do you mean by the heterogeneity, homogeneity, and where to check in, and what is the meaning of the effect size. All these things I discussed without giving you any formula. So because madam told me that there are participants who doesn't have background of statistics at all, and there are participants who are having background of statistics. Now this part will be for those people having background of statistics. And here I will discuss about some procedures, how the weights are being computed, how the estimates are being computed based on the restricted maximum likelihood estimates, and all these things. Not into details because you require a rigorous mathematics, but now this is for those people who are aware of statistics, basically. Okay, so meta-analysis is a process of combining data from multiple studies for the purpose of integrating the findings. And pharmaceutical companies use meta-analysis to gain approval for a new drug because they know already the outcome of the old drugs performing meta-analysis, and they can take the approval of the new drug. If it is closer to that, they can always take. If it is closer to the common number, they can always. For example, you can see a COVID-19. There are many you say immunization. COVID shield is there, Covaxin is there. Then there are now there are two other medicines which are coming up from Russia and US, right? So all these are there. Now, if you do the meta-analysis on all these, how many antibodies have been developed, and how many people have developed antibodies, and let's say there is a common number, and then any pharmaceutical company is designing a new one, and if that it is taking a, let's say, trial of a few people and looking at the antibodies, and it is close to those which other medicines are giving or which other immunization are giving, so that means you can go for the approval. So that is how the meta-analysis is important. So pharmaceutical companies use meta-analysis to gain approval for a new drug, as they can compare their product with others. Then clinicians use meta-analysis to determine the most effective course of treatment. Already some treatments are available. You have the combined effect of most of the treatments. And now you want to see which one is the most important, right? Then sometimes you can perform meta-analysis and choose one of them. Then researchers use meta-analysis to plan a new study in the context of the prior studies. So all these are important applications of meta-analysis. And we perform meta-analysis because we often have a lot of information from many studies, sometimes contradictory also. As I mentioned that in some studies, the correlation was negative. In some studies, the correlation was positive. What do you conclude overall? There are contradictions. So meta-analysis offer a tool to investigate this. It may increase substantial power because many studies, those who are having less sample size, they are lacking power. But if you combine the studies together, even the study which is having less sample size, their effect can be neutralized, and statistical power of overall results can be improved. Then it may answer questions which cannot be answered by the individual studies. So protocol for meta-analysis is very important. First of all, you have to define the research objectives. To assess the overall evidence of the effectiveness of the, see, one of the channel, which is called the calcium channel blocker, CCB, is generally used in the treatment of hypertension or blood pressure. Hypertension is all mild to moderate blood pressure, which is called CCB. The question is how you can address this issue, because there are people suffering from hypertension. But how do you measure this blood pressure? If person is sitting on a bed, the blood pressure may be different. If he's laying down on a bed, the blood pressure may differ, right? So there are different ways. You have to define a proper protocol. That's why we look at the protocol for meta-analysis, defining research objectives. So to assess the overall effectiveness of the evidence of effectiveness of the calcium channel blocker in the treatment of mild to moderate hypertension. Now, this is what is called intervention. I think Dr. Sukhmani was asking about this is what is called intervention. So whether this intervention will be helpful for the patients or not, right? So, however, mild to moderate hypertension definition may vary from study to study. It may vary from study to study. What are the problems? So there is need to specify what do you mean by mild to moderate. For example, if you see the early 19th era, now the blood pressure, you know, standardized blood pressure, we know that between 80 and 120, systolic and diastolic blood pressure, 80, 120. But if you see the previous literature of 1990, people were going from 70 to 130 or 140. So you need to define what do you mean by moderate to mild to moderate clearly. So it has changed over the years. The definition has changed over the years. You see in the COVID vaccine, you see previously it was given when it was given initially, and then it was said that you can give the second dose after 4 weeks. Then it was up to 8 weeks. Now it is 12 weeks. So it is changing every time, depending upon how many people are going through the studies. Hopefully you understand what I'm trying to say, right? So you have to be very, very clear too, because it has changed from time to time. So it has changed over the years, and effectiveness measures or outcome, since the BP varies with position. If there is a sitting position, you can have different blood pressure. If there is a standing position or there is a supine position, you can have different positions. And some studies also report what is called MAP. MAP is called the mean arterial pressure rather than systolic and diastolic blood pressure. So they look at the mean arterial pressure. Now, in some studies, you have MAP available. In some studies, you have systolic blood pressure. In some studies, you have diastolic blood pressure. Question is how to combine all of them together, right? But we require the same outcome for each study. If you want to do a meta-analysis, you require basically the same outcome. So types of control group and control group also matches. For example, let's say I have an experimental group, then I have taken a control group. But in experimental group, all the patients are from age group, let's say 50 to 70 years. And in control group, all are younger people from 20 to 40 years. Now, it is not a control matching. You have to be very, very clear what type of control you are taking in your studies. So control should be matching placebo, or it could be another standard drug. Then also in meta-analysis, design is also very important. Which type of design you are using, whether you are using parallel design, whether you are using crossover design, whether you are using balanced design, unbalanced design, single or double blind. So all these things are required, right? All these things are required before conducting the meta-analysis. These are the prerequisite of meta-analysis. Then obviously, if your data is on patients, then what is the age range, race, ethnicity, gender, inclusion, exclusion criteria of patients, length of the study, because some studies may be only of length 6 months, some may be of 1 year, some may be 2 years. So all these things are required to understand. These are the, if you don't have any data related to meta-analysis, you can go through these websites. And one of the website very important is PubMed. Everybody knows PubMed, and Embase is another website. Then Web of Science, then Clinical this clinicatrial.government, they have a lot of data where studies have been performed. You can pick up the data and go for meta-analysis. Then NCBI side. Generally, you see NCBI is by NIH, National Institute of Health, and NCBI sites, they also have the data for many studies. And we Professor Kanchan Jain, myself, and Savita Jain, we pick up the data basically from one of the sites of NIH, of NCBI on AMD, age-related macular degeneration. And I'll show you the results of that particular, because it is being published. So I'll show you the result of that also. And recently we have also developed two websites. One of them is called Cancer PDF, and another one is DisFace. And DisFace is another website. It is still to be put on the public domain. This is already on the public domain, because there are certain issues related to this. The candidate who has done PhD with me on this face, that means how to develop a full face from half face. Let's say you are going to the ATM and there is a camera on the left hand side, so only half of the face will be captured, half of is not. Then we have developed a technique using bioinformatics approach, and how to develop a full face from the half face. It is not using camera trick, it is using bioinformatics approach. So these two websites are also important. They are involving different kind of studies. And this is the website, actually, you can go through. Okay. Now, somebody was asking about how to choose weights and all these things. So there are two models, as I mentioned. So this is a little bit theoretical aspects. And those who are not familiar with the statistics, pardon me, please, because some theoretical aspects are also required before coming to the final practical demo. So major assumption for fixed effect model is that all the studies in the meta-analysis share a common overall effect size, which is hardly achieved in practical situation. Say the same impact for all other risk factors. So it is assumed that for the IR study, you can use this notation. This is the effect of the global 2 effect theta f across all the studies. So this is the same for all across the studies. And these are for your different studies. You are getting estimates, but they should be close to this. So that is the idea of this fixed effect model. And this is the model that this is equal to this plus this. This is having normal distribution with variances can be estimated, and variances are generally estimated by this formula. So how to get the weighted estimate? So as I mentioned, there is a mathematical formula. You get the estimates. So there is a simple weight. You get the estimates. You have seen the estimates, they are given in forest plot. You simply add those estimates, divide by the total number, you will get the estimate of that, overall estimate, right? And in this case, variance of this will come out to be this, with this will be the confidence interval, which we have drawn on that line. But this is only for fixed effect. And generally in fixed effect, we don't use the simple, we use the weighted average actually. And weighted average formula, we compute the variance of this, then weights must come out to be 1, and then we compute this by using this formula. And how the choice of weights varies, all these things are also written in our paper. You can go through that paper. And there are different choices of weights. One of the weights one can choose, many people also choose, look at the total sample size of all the studies and 1 by n, take that as weight. Another is you look at Ni over n, where Ni refers to for each study, the weight will differ because Ni is number of person in subject I divided by total n. And then this is another way of looking at the weights. But the globally used formula for fixed effect size is basically this one, which is 1 over the estimate of the variance, considered to be the ideal for most studies if you are using fixed effect. So these are the choice of weights with different formulas, and there is a statistics whether the overall mean is 0 or it differs from 0. Then random effect model. The random effect model, as I mentioned, that in 90 to 95% of the cases we use random effect model, right? It's an extension of a fixed effect model. And here the treatment effect varies from study to study. The treatment effect varies from study to study. It is not same for all. The effect size is not same for all. Okay. This is the random effect model is denoted by this. And this is this theta IR. R is written for random. This is theta R, the true effect plus some errors. So this error and this errors. Now, why there are two errors? Because this is 0 with this variance, this is 0 with this, describe the within center and between centers. So we take two types of errors, between and within. So there are two types of errors and they are generally normally distributed, and we get the estimate of delta R square. So this is the formula to get the estimated weighted mean. Estimated weighted mean if you are using the random effect model, right? And these are their confidence intervals. And if you take this part as 0, then obviously this will coincides with your what is called the fixed effect model. Okay, these are different statistics. I have already shown you these statistics. We compute delta R square by this, Q by this, V by this. Of course, there and here the notations are totally different. And this is what is given in the package of R. You can go through that metaphor. And in metaphor, there is a restricted maximum likelihood method, which is given. So this is considered to be the best method to estimate the overall effect size as well as estimates for different studies. Okay, then finally, we have to go for the mixed effect model. Now, where to use mixed effect model? Mixed effect model is basically a combination of fixed and random effect models. There may be some studies which are having the common effect size. There may be some studies which are not having the common effect size. In those situations, particularly in longitudinal studies, this thing can happen. And in the area of biological sciences, sometimes in social sciences also, medical sciences, there are longitudinal studies. And generally mixed effect models are used for longitudinal studies, right? Because over a few years, the effect size is same, but after a few years, it has changed. Now it has a new effect size. So in such type of situation, and I want to do meta-analysis by combining all the studies, some previous studies, some future studies, then we use what is called mixed effect models. Okay, and you see, sometimes we can go for the comparison using ANOVA and all these things, but believe me, meta-analysis is a better way of doing all these things. This is the model for mixed effect, where this is the true effect and the value of the jth moderator. Generally, we apply mixed effect models with the help of what is called moderators. Yeah, what is called moderator. So I will show you in my last part, giving you a practical demo, how the moderator are being used. Okay, now I'll just take 5 minutes and then give you a break. What is comprehensive meta-analysis? And what is the advantage of this over other packages? Because although it is a paid software, they have put in a lot of efforts, and there are hundreds of formats given, hundreds of formats. While if you look at Meta Essentials, while you look at Review Manager, only limited formats are there. So comprehensive meta-analysis is a very important software. I have worked on this, and I'll show you some important things here. For example, this is one study which is involving subgroup within study, male and female, male and female, male and female. This is treated, total number is here and treated. And after that they died. And in control also, they were not treated, but they also have died. So there are two groups. You can call this as experimental group. You can control this as control group. It has computed the odds ratio. Then it has computed the log odds ratio, standard error, risk ratio, then log risk odds ratio, and their standard errors. Now, what is the important point in comprehensive meta-analysis? So simply enter data into the white columns. You enter the data in these columns. There are white columns. Once you open this, it will appear like this, because you will be choosing your format. Let's say I choose format of experimental and control. If you choose the format of experimental and control, immediately this format will appear on your screen. And you simply enter your data, right? And if you are choosing, let's say, experimental and control, but with respect to mean, SD, and number, then another format will appear, and you enter your data accordingly. So simply enter the data into white columns. Then the program computes the effect size. So this is basically the effect size which is being computed. Then there are conversions of this into logs, into risk ratio. All these are there. So compute the effect size and display in the yellow columns. So all the effect sizes are displayed in the yellow columns along with the confidence intervals and all that. Very simple to operate in comprehensive meta-analysis. Let me tell you, we have published a recent paper on diabetes with one of the person from working in a hospital. And I did the data analysis on that diabetes paper. It has appeared in scientific review, and I can send you the link also. Systematic review, not scientific review, systematic review journal in diabetes paper, when we have done the entire analysis using comprehensive meta-analysis. And I was performing the analysis, and what happens, it expired in between. Then some part is taken by review manager. But anyhow, okay. See, enter the data in more than 100 formats. For example, events and sample size in each group. You are given events and sample size. For example, how many events are there, total number and sample size. Then you can use. Then known events in sample size, then make in terms of chi-square if you have match 2x2 table, in terms of exposed or unexposed problem. So there are hundreds of formats given in comprehensive meta-analysis. So based on your study, which kind of study you are performing, choose the appropriate format, and that particular screen will appear, and then enter your data. And once you enter your data, the entire summary will appear without even pressing entry, right? Such a fast software. So this is what you are doing. Now let me show you the application of this. See, there are studies here. Out of the 14 studies, 10 studies are there, which are cohort studies, where the treated number, control, and experimental group is given. The events are given, and those who have died, they are given, right? Obviously, this will be blank because we don't have the data related to odds ratio. While in rest of the 4 studies, you are simply given odds ratio. You are simply given odds ratio and the lower and upper limits and confidence levels. You are given here. Now you see how beauty of this comprehensive meta-analysis. Some studies are there which are having different format. These are the studies which are having based on odds ratio. Similarly, you can have studies, you can have third set of studies which are based on mean and SD. But all of them can be entered into one format. You see, this is the format for odds ratio. This is the format for events and how many have occurred. And then third format with white color will also appear with mean and SD. So you enter your studies there. So here, studies 1 to 10 reported the number of events and total n in each group. Then this is not available for these 10 studies, right? And while 11 and 14, they just report odds ratio and confidence intervals. You see, these studies, they report just odds ratios and confidence intervals. And you have to perform meta-analysis on this. And these are the effect sizes which have been obtained. Whether they are coming from this, whether they are coming from this, it has computed all of them, you see. And the program computes the effect size and the standard error from either format. So all the studies can be used in the analysis. So using different formats, people have conducted different studies, they can be used, all of them together. So that is the idea of comprehensive meta-analysis. And I'll give you a practical demo on AMD data and some other data sets. Maybe we can take a break of 10 minutes. If anybody is having questions, you are most welcome to ask, please. Yes, please. Any question?
Yes, any questions? You can write it out in the chat box.
You can write in the chat box, or you can unmute yourself and ask me, please. Yes, please. Anybody can ask, please.
Yes, I will share the feedback link once the session is over.
So, Sumit, sorry, आपका नाम मुझे भूल गया. Surat, sorry. Surat, can we take a 10 minutes of break and come back? Is it possible?
Yes. Yes.
So
yes,
you can announce what time. I mean, I'm not going to switch off because I'll not
sir,
do anything on this. I will do a practical demonstration now.
Sir, 12:30 sharp will join.
Sure, no problem. So 12:30 to 2 o'clock, will that be okay?
12:30 to 2 o'clock.
Practical demonstration.
Yes, and if required, you can extend a little.
depending upon, I think I'll be able to cover within the limits, hopefully.
Okay. But if
So,
required, you can. You are because nothing is there after that. So
okay, all right, all right.
So
So
it's possible.
yeah, I will discuss 3-4 problems and practically doing meta-analysis using R.
Yes, sir. Yes, sure.
So I
And
request all
there
the
will be
participants.
only single feedback. All of you, please pay attention. There will be only single feedback at the end of the session, not prior to that.
So the
Okay.
feedback form will be at 2 p.m., not now, at the end of second session rather. Okay.
So don't leave, please, in between, and you can have your systems on. And I'll be back in
10
another
minutes.
10 minutes. 10 minutes.
12:10 is there. 20 minutes, sir. Let
Yeah,
it
20
go on
minutes.
to
I think it's better to give a break of 20 minutes.
Yeah.
People can enjoy a cup of tea and come back. And
Yes,
still,
sir.
if you have any question, you please put into the chat box. I can answer. Okay. So shall I depart for a cup of tea?
Yes, sir.
Yes.
Sure, sure.
Okay. शुरू करें मैडम?
Yes, sir. Yes, sir.
Oh, just give me 1 minute. Just give me 1 minute. I'll
Yeah,
be back.
sure.
I am back now, ma'am. Hello.
Yes, sir.
Shall we start?
Yes.
Okay. Now, so far, I discussed all about the basics of meta-analysis, how to look into heterogeneity, how to look at the interpretation of the forest plot, what is funnel plot. So all these things you have to keep in mind, because now we are going to give you a practical demo using a software which is called R. R has a lot of flexibility. It's a free software. Generally, many people are using R now, and the same thing is available on Python too. So you can, if you know Python, you can run the same program. I mean, little bit changes can be made, and same program can run on Python. Okay, so I have created a folder here. Just my screen is visible, huh?
Yes, sir.
So, and I kept all the data sets in this folder. So first I will join the reason, because if you create a folder on your desktop or wherever you want, then you will not have to give the path every time. If there is a file, you can directly access that file. So that is the advantage, that you can create one folder.
Sir,
folder
can
here.
you share that folders in the that I think so few wanted to work along with you? Or what you will say them? You will suggest them to work
It will
later
be
on,
difficult because there will.
demonstrate, and then
I
they.
think what I can do, I'll give them the program, and
Okay.
I'll give them the folder also later on,
Okay.
and they can work, because it will work. Then program will be there and data files will be there.
Okay.
Right?
Or otherwise, last moment I can share. If you
Yeah,
will email
you
me,
can,
I will
because
group. I will
so
put up. So
only thing is
can
in this
run.
meta, there are some other files which are not required. So I'll keep them out and then send it to you.
Okay, sir. Fine.
All right. So this is the meta. I'll show you some data sets, and then we will go for the practical demonstration of the meta analysis. So for example, first of all, we'll go for a very simple analysis using meta analysis based on correlation. For example, very small data set, let's say these are the studies conducted by 6 people, and they have given the correlation R and the sample size also N, right? So question is, how we can combine all these studies together? Is it visible, madam? Is it visible? Or I can increase the size from here.
Yes, sir. It is visible.
Now you can see maybe. I just increase the size. Now you can see we have 6 different studies by, these are the names of, and they have, based on 2 attributes, they have obtained their characteristics, you can say, the values of R and values of N. Question is how we can combine them together to get a single number. So this data set I'll use. So there are only 2 things. One is R, another is N. And we'll look at the forest plot interpretation, you already know. So just closing this file, please remember that this file, okay. See, all these files are here, and I'll show you another file before, otherwise I have to come again and again. So that was the correlation file. Then we will do one experimental and control, and that will be, I'll be using this one, not this one. This one. So here you have one experimental group, another is a control group. Then you see, I'll just explain you the data set so that you can easily understand what I'm trying to say, because I'll be using all this. See, there is a experimental group, control group. There are 13 different studies. These are the events which have occurred in experimental group. And out of the total, you see, either this is called a binary event. Binary event means you can convert this table into 2 by 2. For example, 2 by 2 means if on row wise, I'll write experimental and control. On column wise, event occurs and not occurs. So you can then classify into 2 by 2 table. So here the events, total number of events in the experimental group is 50. And out of 50, how many events out of this 50, how many people have maybe has some problem? So 20, that is the event has occurred. And those who have not occurred is 30. So that the total is 50. So that way you can understand 20 plus 30 is 50. Similarly here, 25 and 25, 50. So if you add these two, it will come out to be this thing. This is in the experimental. So I put the word EXP, EXP. EXP means this is the total of experimental group, number of events. No, where nothing has happened in the events group, and here events have happened in the experimental group. So this is the experimental group, these 3 columns, and the similar columns are there for control group. So here in control group, how many events have happened? And this is the total number. And if you add them, then this is called. So this type of data is being analyzed because it is a binary. Either the event has occurred or not occurred. So this kind of data is being analyzed by using meta-analysis, giving a command which is called meta-bin. Meta-bin means that you are using the binary information. Either the event has occurred or event doesn't have occurred. So this is called meta-bin. And earlier was the correlation data. And in correlation, we generally used meta-core. The command will be meta-core, right? Then the third data set, let me show you that also. We will be using, which is based on mean and SD. So mean and SD of the experimental group. So there are few studies here. We have mean, standard deviation, and number. So here we have the number of, E stands for experimental group. So here you can see, this is the third data set I'll be using. It doesn't matter whether you have 8 studies or 7 studies or 18 studies, analysis will be same. It is just for demonstration point of view. I have taken a very small data set. So this is the number in experimental group. This is the mean SD. All these 3 columns are for experimental group where E is given. And these are the similar columns for control group where N is given, mean is given, and standard deviation is given. So we will be analyzing this data also. And then finally, the last will be, which is having some, the last data that will be used will be AMD data. You see, there are 20 different studies, A to T, and here the treatment positive, treatment negative, then in control positive, control negative, and these are the weights given. These are the weights given, right? Sometimes even if weights are not given, they can be computed also. But these weights I have kept in to go for the meta regression. So I will be using these weights, and sometimes I'll also use this year. So whether there is a year-to-year variation or what is the impact of weight on all this. So here you can see a treatment group and a control group, but these numbers will not add up to anything, right? So this is out of the control, this is out of the experimental group. So it is not a binary. It's not a binary. So we will be using all these 4 data sets to show you how to perform meta-analysis. Okay. So I have this meta-analysis. I'll be using RStudio because in RStudio, it's easier to work with. You can write the program here and then you can get the output here and the graphs here. Those who are not familiar with R, don't worry at all. Those who are not familiar with R.
Sir, even they can work on our collaboratory, which is Google, directly on Google Cloud. It's run by the Google Cloud.
Yes, they can work on. Yes, definitely.
And once they will press the run command, they will get it directly.
They will get the result. Yes. So anyhow, so meta-analysis using RStudio. So as I mentioned that I kept all the data in a file. There is a folder on my desktop, which is called meta. So first thing in R is to connect to your folder. And to connecting to your folder, there is a command in R. Those who don't understand command, please, if you run with me, I mean, you try to follow me, you will be able to understand everything. This is called set working directory. So set working directory, if you go to your meta folder, right click, there is a properties. In properties, there is a path. You copy that path and paste it here. I just did that. I paste it here so that you are into your directory where all the files are available to you. So set working directory. So set the working directory. And if you want to see you are in which working directory now, that is called get WD, get working directory. So if I want to see I am into the correct directory or not, so it will give you the answer that you are in this directory already in meta. So we are at the right place. So that means we have connected to our directory. Now, what is the advantage of connecting to the directory? I'll not have to give the every time now path. Whatever the files are there, I can easily access from there without giving any path, right? Okay. Now for meta-analysis, first of all, we will do the meta-analysis for correlation data. Then we will do the meta-analysis for binary data, where the total was adding up to the entire overall total. Then we will do the meta-analysis for mean SD data. And finally, well, we will do the meta-analysis for AMD cases. So 4 data sets I have chosen, and I try to give the interpretation and everything. And the last part will be very important if you can understand that part. So I need, first of all, three important packages. One of them is called meta. So there are 2 ways to install packages into R. One is you can go to tools and there is a install packages. And in install packages, for example, I want to enter this meta. You just write down meta here and your net should be connected. Just press install. Or if you write command, then you have to write install.packages meta, right? It will be very basics for those who are already working in R, but because we have to take care of those people who doesn't have any knowledge of R. So I'm just saying that either you write this command or you can go to tools and write down the name of the package here and then press install, right? So anyhow. So, and to run any command, this is the run button. You place your cursor anywhere on this, anywhere, and it will run. So this is running. So it has installed the meta package, and then you take this meta to the library of R. So this is in the library of R, right? So it is loading in the library of R. Similarly, we have to take one package which is called RoboMeta, although it is not required, but sometimes it's better to load some other dependencies which you require, so that you should not face any difficulty while analyzing the data, and take this to the library also. Then the main package for meta-analysis is called metaphor. And here I have written dependencies is equal to true. What is the meaning of dependencies? That means if it requires some other package, let's say it requires a matrix package or some other package, so automatically first that package will be loaded and then metaphor will be loaded. So this is the what we mean by dependencies. So just click onto, and then it's already, I think, loaded in the matrix. It requires package, doesn't matter. And then this package also deploy. All the packages are being loaded. Just wait for a moment. And now here. And to do the correlation analysis, we need, of course, it's a part of meta, but sometimes I have seen errors also. So better to load this one also, MetaCore. MetaCore is for correlation analysis. Then library MetaCore. Okay. Now, if you remember, our data was in one of the files that is called correlated meta. And it is all, whenever we enter the data in Excel, you convert the Excel file into CSV file. You know how to convert into CSV file. And once you convert this into CSV file, then the task becomes easy. Otherwise, you can directly read Excel file also, but for that you require another package. But if you convert this to CSV, you don't require any other package. So this is the command read.csv. That means we are reading the CSV file, and our file name is, if you see in the folder, the file name is correlation_meta, but don't forget to put this CSV. Otherwise the command will not be accepted. So click onto this. And if you want to see the data, it's a very small data set, you can see. Now it is in this file from, you can see on the console, study is there, 6 people, R and N, right? So all this is here. Then now, because there are different variables, one variable is study, another variable is R, another is N. One way is to extract these variable. And if you don't want to extract these variable, then you can use the attach command. If you attach the data, variables will automatically be extracted. So this is the attach. Now we will run the command. So we have only two. One is R, another is N, and our data is given in data. So this is the command. So I'm just writing model. You can write M or whatever you feel like. So meta correlation, that means we want to perform meta analysis on correlation data. We want to perform meta analysis on correlation data with R and N. Only two things are required, and data is given in data file, right? So run this. So it has run. Now I want to see the output. So if you want to see the output, then the entire output has appeared. You see, if you remember, we will go for the plot also, forest plot. But before that, your forest plot, the estimates have been computed. All the estimates have been computed, and these are your correlations, and these are their confidence intervals. This is the weights which have been assigned by using fixed effect. And these are the weights which have been assigned by using random effect. As I mentioned, those studies which are having larger sample size will be given larger weights. If you remember, this study was having sample size as 400. So it has been given larger weight, right? And that is the drawback of fixed. but number of studies here is 6. And if you are using the fixed effect model, then this is the overall summary. This is called overall summary effect. This is the overall summary effect. And we have to see whether the overall summary effect is same or it is different, right? Overall summary effect is significant or not. So you can see the p-value is less than 0.001. So that means this is overall significant. It is significant, and it is based on z value. If z value is more than 1.96, result will be significant. And similarly, if you are using random effect model, then overall effect size combining all the 6 studies is 0.4875, and this is coming out to be 0.27 confidence intervals from this to this, and again it is coming out to be significant. The question is whether heterogeneity or homogeneity is present or not. For that you have to see what is the value of I-square, and I-square says that the value of this is 86.2%. so that means the heterogeneity is there. And how to test the heterogeneity? There is a p-value also, that is called test for heterogeneity, and it is in terms of Q, which is called Cochran Q. And Cochran Q says that the value is coming out to be 36.14 with 5 degrees of freedom, and it is significant. So all these studies are not similar. They are having different effect sizes, and moreover, the overall size is coming out to be significant, but there is a heterogeneity. So if there is a heterogeneity, there is no idea of going for fixed effect model. There is no idea of going for fixed effect model. You can simply go for the random effect model. And you will see that in most of the cases, we go for random effect model, 90 to 95% of the cases, as far as the literature is concerned. Only in few cases where some specifically it is mentioned that you have to apply fixed effect, then you have to. Okay. Now, as I mentioned, we have to simply apply the forest. Our entire data is here in model. So forest model, if you give one command, you will get the forest plot. It's very simple in R. And now you can see the forest plot. And to see the clear picture, you can zoom it. And if you zoom it, you can see very clear picture. See, is it visible, madam?
Yes, sir.
Okay. So these are the 6 studies, and these are their numbers, if you remember. Then there were correlations, 0.5, 0.6, and all this. Zoom. And if you see, these are the confidence intervals, all confidence intervals. If you are using a fixed effect model, then these are the weights. I have told you the formula how to compute the weights for fixed effect. And if you want to see why this study has been given weight as 61.4, why? Because this is having a larger sample size. There's some problem, low disk space. Anyhow. Then if you see the next one is 90. Next one is 90, and this has been given a weightage as 13 points. So you can see weights of fixed effect varies with your sample size. The more the sample size, more the weightage is given, right? And then if you look at the weights of the random, they are almost same. Their range is from 15 to 20, almost, or 13 to 20, right? Because, and moreover, we have seen that there is the Q value is coming out to be significant. So rather than going for the fixed effect, we have to go for the random effect model. So there is no idea of going for fixed effect model. We have to go for the random effect model. So there is a command, you can remove the fixed effect, and we can go for the random effect model, right? So rest of the interpretation, you know. So overall result is coming out to be significant. Overall result is coming out to be significant. And there is a significant effect of intervention on our study. But correlations are different in different studies, right? But overall, it is, this diamond says overall. And overall, if you are using the fixed effect, this is the overall effect, 0.36. But if you are using random effect, you see there is a lot of difference between random and fixed effect. Because, why? Because your task value is not 0. If this would have been 0, these two are almost same. right? So there is a between variability, because toss care is 0.0819 and it is significant. So that means there is a between variability is there in the studies. So that is the idea of, I think the entire interpretation is clear. And here is the zero correlation. All the correlations are positive. Overall is also coming out to be positive. So very simple analysis for correlation. And sometimes we also,
It means there is a gap between these studies. You mean to say that, and it is
yes,
leading finally to the conclusion that all these studies carried out, they were not one and the same. There is a lot of
there is heterogeneity is present.
Yeah.
Heterogeneity is present, and further there are tests for heterogeneity. We can go for funnel plot and all these things, which I'll go in the subsequent analysis, right? Which I will do later on. Okay. So that is the first simple analysis. So you have an idea that only 2-3 commands can give you the answer for correlation. All right. Now we'll go for the next data set. And that data set is relating to binary. Meta-analysis for binary outcome. Now in binary outcome, if you remember, that was experimental and control group. You have the events from experimental group, total of the there. So those events have occurred or they have not occurred. Similarly, in control group, events have occurred and they have not occurred, and you have the total. And the entire data was captured in this file. That was experimental control CSV file. So let me read that file. I'm just reading that file. And since this file is having many studies, so I'll just put head. Head data means first 6 columns will be displayed. So you can see the first six columns, so that you can easily read. First is a trial number, then experimental control. So here is the total number in experimental group is 50. Out of that, 20, in 20 cases, the event has occurred. In 30, it has not occurred. No event. Similarly, in 50, 25, 25. And same way, if you add these two numbers, I have already explained. Similarly, in the control group, same thing will happen in the control group, 45 plus 7, 51, right? And if you see the summary of the data will give you an idea about the how many variables are there, what is their minimum value, maximum value for each variable. So quantiles. So that will give you the summary of each and every variable. And which type of structure it has. It has a structure of data frame. So because we have imported the data frame only with 13 observations, there are 13 studies and 9 variables, right? And some of the experimental and control, because the name is given active and control. So they are character variable and rest of them are integer variables. So it will give you the entire information about the data. That is called structure. And if you attach data, you will not have to extract variables. Otherwise, every time you need to extract variables out of your data. So for example, let's say I want to extract this variable, which is event experiment, right? So what we generally do in R to extract, let me do it here. So this, then our data is in data. So I'll write data and then use the $sign and then control V. Same. Now it will extract this one because it is available as a matrix in the total data frame. It's a data frame. Your individual access is not there with you. Individual access, you can either you use for each variable, you have to use this command for each variable. I have just shown you that how you can extract the name of the file, $sign, and the name of the variable. And name of the variable can be kept at same. Now this event experimentally separate column with you. Otherwise, it is in a data frame. Okay. Or better way is to go for attached data. So just attaching the data will not require to extract each and every variable. That is the idea of attaching this data, right? Okay. All right. Now, as I mentioned that there are either events are happening or they are not happening. It's a binary. So for binary, generally we use compute two types of summary measures. One of summary measure is called odds ratio. Another summary measure is called risk ratio. So I'll show you the result of both of them. These are all the variables. I mean, event in the experimental group, total number in the experimental group, and even in the control group, total number in the control group. All these things are here. This is what you require. And then your main title is trial, that is here. And then summary measure I am using is OR. If you replace this by RR, it will give you risk ratio, and data is in data, right? So try to explain you the terms which are being used in this. So this will, what you will get, actually you will get the results in terms of, because everything is in the 2 by 2 table, either the event has occurred or not occurred in experimental and control group. So it is in 2 by 2 table. And for 2 by 2 table, either we compute risk ratio or odds ratio. So if you compute the odds ratio, so the command used is meta bin. Meta bin means binary, on a binary event. Just like in the previous analysis, we have meta core. Meta core means for correlation. Meta bin means for binary event, right? And then you run this. So it has run. And if you want to see the data, either there are two ways to see the data. Either you use fixed data or you use view data. So either you use this command, or if I use this, you will see just like an Excel file. The entire data will be here. You see, entire data will be here. You can see at a glance. Or you can write capital view, capital V, view data. Let me show it to you. If I write VIEW and data, you will see the entire data like this. You see, again, experimental control, then you have events in the experimental group, control group, you can see the entire data here, and then close this, right? Okay, now we want to check what is our results. OR meta. OR means based on the odds ratio. So run this, and the entire information is here. So these are the weights. There are 13 different studies. These are odds ratios with the confidence intervals. Then you have the fixed weights. Shift it here. Then you have fixed, if you're using a fixed effect model, these are the weights. If you're using a random effect model, these are the weights, right? And here is the entire summary. The number of studies combined is 13. And these are the odds ratio. And odds ratio for fixed effect is 0.47. And random effect is also very similar, you see, 0.4750. There is hardly any difference between the two. Why? Because if you look at the I-square is coming out to be 0. I-square is coming out to be 0, and value of tau is 0. And if you remember one of the slide, I mentioned that if the value of tau is 0, then the results based on fixed effect model or the random effect model, they are almost same. And now the overall effect is significant. That means there is a significant effect of intervention in experimental and control group. This is the entire conclusion. So there is a significant effect of intervention in the experimental group. So intervention has played a major role because it is coming out to be significant, both by using fixed effect model or random effect model. Now, some people ask me whether I should report fixed effect model or random effect model. You can report both of them, because somebody should be clear that heterogeneity is not present. Why heterogeneity is not present? Look at the Q value. Q value is 7.6, degree of freedom 12, and P value is non-significant. So that means there is no heterogeneity. In previous case, there was a heterogeneity present. So you can report both the results. It's up to you. Or you can mention that the heterogeneity, if you have lack of space, you can specify your fixed effect model. No problem at all, because this is coming out to be non-significant. So all depends upon on you, how you want to present the result. So you can check. All right. So now we will go for, this is the results based on odds ratio. Hopefully the output is clear to you. And you can go for the summary of the odds ratio also. Now, if you go for the summary, then in summary, this part will not be shown. Only you will get this summary. Only the summary, statistical summary you will get, but not the data itself. That is the difference between this command and this command. So let me use summary. So you can see in summary, you have the rest of the things which are statistically computed, but not this one. This part will not be there. Okay. So that was for odds ratio. Now, similarly, we can compute risk ratio. So if you are using risk ratio, then we will plot the plots also, and we will see the result. So risk ratio, now what I need to change, I have the same copy from here to here. What is the difference? I just changed the summary method. The summary method is now RR. That means the risk ratio. Summary method is RR. Rest of the things are same data, everything is same. So just click onto this. Now it will give you in terms of risk ratio. So it has run, the command has run. And now if you see the risk ratio, the entire information is here. Now these statistical estimates are a little bit different from the odds ratio. You see 74, 0.74, 0.77. But important point is, again, we have to go for the test of heterogeneity. Test of heterogeneity is again coming out to be non-significant because there is hardly any difference between these. 0.74, approximately this is 0.75. This is 0.77, right? And effect sizes are coming out to be significant overall. That means there is a effect of intervention in experimental and control group, right? And if I use the summary RR, you will get without the data. So all the summary here. Now let's plot the forest plot. So if I want to plot the forest plot, first of all, forest plot for OR meta. So you see, this is random is equal to true and combined is equal to true. Combined is equal to true. Let's say I want to get only for one of them, you can put fixed as false and this as true, right? So forest plot, you see, this is the forest plot. Let me zoom this, that will be better. So here is the forest plot. Fixed effect model, random effect model. This is for odds ratio, right? And your heterogeneity, there is hardly any heterogeneity. All these studies are almost similar. All these studies are almost similar. That you can also check with the help of this mean line. And in odds ratio, as I mentioned, your main line will be placed at 1. Let's say if all these boxes, they would have been on this line, what could be your interpretation? Your interpretation could be that there is no effect of intervention. Why? Because this is 1. 1 means if odds ratio is equal to 1, that means experimental and control group, they are virtually same. So there is no effect of intervention. But here you can see this on the left hand side, it is showing the effect. On the right hand side, it is not showing the effect. So you can see there is a effect of intervention. There is a effect of intervention. You can see that. And the effects are coming out to be significant. This is with random model. This is with fixed. In both the cases, we are very close to each other because task here is 0. And heterogeneity measure is non-significant. So that is the interpretation of all the studies together. All right, this is for odds ratio. Let's do it for risk ratio also and see how does it differ. This is forest plot for, you see, forest plot for risk ratio. Okay, run this. And you can see zoom it, and you can see now instead of odds ratio, we are having risk ratio. And the entire thing is in terms of risk ratio. Weights are there for random, for fixed also. And you see here also p-value, sorry, values are very, very close, 0.75, 0.77, the overall effect. Whether you're using fixed or random effect, in such type of cases, better to specify both the models, fixed as well as random. Now, sometimes you may be bothering why there are 2 lines only. Why there are 2 lines? Because one line is for fixed effect model, another line is for random effect model. That's why these are the 2 lines, right? And this is the one, there is no effect line. So no effect line, no studies on this. Most of the studies are effective, and the overall it is effective. Overall it is effective. So that is the idea of looking at the all these plots. Okay. Now, since there is a homogeneity, and let's look at how the funnel plot look like. How the funnel plot look like for odds ratio. So if you see the funnel plot, very vague funnel plot. Why? Because this is not the correct way of plotting the funnel plot. Funnel plot is just based on inverse of the variance, while it should be based on actually standard error. So there are a lot of options in metaphor. You can plot funnel plot based on different point of view. Instead of standard error, instead of inverse standard error, instead of size, best funnel plot is given by standard error. So let me plot the next one. And that is the funnel plot you have to report actually. So this is the correct funnel plot which you need to report. And if you see the zoom picture, most of the studies are here. No study is outside this band. No study is outside this band. Right? What does this mean? It's just like a pyramid. It's just like a pyramid. So some studies are on this side, some studies are on this side. No study is outside. No study outside means there is hardly any publication bias. If there would have been one or two studies, let's say somewhere here or here, you can expect a publication bias. And we have already seen that it is almost homogeneous in nature, and all these studies are more or less homogeneous. That's why there is no publication bias. There is no publication bias. So these are the odds ratios. And the more it is concentrated towards the pyramid top, that means it is based on the larger number of observations. So it is based on medium number of observations. That is the idea. So curve is coming out to be flatter. So if you look at the curve of this type, let's say, that means there are some studies which are used larger number of sample size, maybe 400, 500, but none of in our case here. So we have used the medium size, maybe 50, 60, 70 observations, right? So that is the interpretation of this funnel plot. And you can see that there is hardly any publication bias. Okay. Then this is for inverse. Generally, we do not go for inverse also, inverse plot. And this is against the size. This is against the size of each study. That also doesn't give you very good. But all I'm showing you because all these options are there in metaphor. Okay. Then you can also get some influential analysis. If you want to see, then write down meta influential analysis of, let's say, OR meta, and you will get some additional information. Additional information means that you omit one study, then what is the effect? If you omit the second study, keep rest of them, then what is the effect? So if you omit one, then odds ratio has little bit impact, but still all the effects are coming out to be significant. And your Tosker value is 0. So rest of the things are same, right? So sometimes we need to look at if there is outlier. Let's say if there is outlier present in your study, let's say one study is totally different from all others. Then if you give this command meta info, so the odds ratio will come out to be totally different for that. And you can exclude that study and then rerun the meta-analysis so that you can get better results, provided that study is not important for you. Of course, it is important. You have to retain that. Then use the random effect model. Okay. So that is the second data set. So we have analyzed two data sets. One is based on correlation. Another is based on binary information. Now let's do the third set of data analysis, which is based on mean SD in experimental group and control group, right? So this analysis will be mean SD, based on mean and SD. Okay. So let me clear this screen. So entire data is given in this mean SD CSV file, and data will come out to be in data1 file. So data1, and if I want to see the data, so this is the entire data. For example, number in the experimental group, how many patients are there? This is the mean. This is their standard deviation. E means all experimental group. C means the number in control group, mean of the control group, SD of the control group, right? So there are 7 studies and you have this. The question is, we have to calculate the estimates. We have to calculate the estimates. And estimates are given in terms of the mean difference in this case. Because if you're using the mean data, your estimates will be in terms of mean difference. And moreover, your forest plot, the line will not be against 1. The central line will not be against 1. It will be against 0 now. And you can check that. And the command, if you're having a mean SD data, your summary measure, this is called measure. Your summary measure, you can write SM or you can write measure. Summary measure will be your standard deviation mean or mean standard deviation, right? Or mean difference. The summary will be based on mean difference. So command which we use to estimate the mean difference is called ESCALC. That means calculate estimates. This command stands for calculate estimates. Calculate estimates of the mean difference. Calculate estimates of the mean difference. So I'll run this command. Now it says there is error. Why there is error? Because we haven't attached the data. We haven't attached the data, I think. Yeah, I have just shown you data. Attach the data because it could not read the variable name. So attach the data one and now give the command. Hopefully, again, there is some error. Where is this error? Yeah, these are now run this command. What is this? SMD. Read the file, data one, all the files are there. Attach data one and compute. I think there is some problem with the, let me see where is the problem. Data equal to data one, NC. Sumit, can you see the problem here? Sumit, are you there?
Yes, sir. Yes, sir.
Sumit, no, I'm asking Sumit Patel. Sumit Patel?
Yes, you can unmute yourself, Sumit.
Yes, Sumit, you can unmute.
There is some problem. Why it is not running? Still wonder. ESCALC, that's okay.
Some packages to be installed.
It doesn't say any package. It says something. Could not find this.
So the problem is like some of the library is not attached. Some of the library is not attached with it. Just run the library. Library जो वाली command है, so super जो command है library वाली. Run those command, meta and all. Meta for.
Maybe.
Yes, sir.
Metaphor.
Yes, sir.
Yeah. Maybe we can run this also. Run it. Yeah, sometimes it happens. But anyhow.
Now you can run it, I guess.
Let's see. Now read the file again. Data, attach data. I think it should come now.
Done.
Now it has run. There was some library problem only. And if you want to see what are the estimates, so here you can see whenever we are having mean and SD type of data, experimental and control, in that case, actually, you will get the effect sizes in terms of YI and VI. What are these YIs and VIs? This is basically the effect size. This is called the effect size of each study. So this is the effect size of each study. And these are the variances. And these variances help us to compute the weights, right? Now, if I want to remove, because I don't require data now, everything is being computed. So it starts from second number to 7 column. You see, this is a first column, second column, second, third, fourth, fifth, sixth, seventh. So I can, row names is equal to fall. I want to retain the row names. So that will give you YI and VI. YI is your effect size that has been computed, and VI the variances of from each study have been computed, right? So if you run this, you will get only corresponding to yi and this. Others have been removed. Minus stands for that you have removed from second column to the seventh column. You have removed all that, right? And now, if you have the mean and variance data, now these are the additional columns which are there in your data now. One is effect size, which have been computed by using this command. Estimates for that have been computed along with the variances. And now you want to fit a model. Let's first of all fit random effect model. So I'm just giving the notation meta.re. Re means random effect. And the command will be random meta RMA. And just specify these two values, estimates and the variance. So yi, vi, data is your data one. Data is data, that one, right? So execute this command. If you execute this command and see the result, you will see the entire results. So all these results are here with the similar statistics. You can see there are 7 studies. Toss care has been computed by using restricted maximum likelihood estimate. I have shown you. And the toss care estimate is this one. Tau value is this. I-square value is a 23.86%. Variability is there, which is marginal. And there is one another statistics which sometimes people generally don't use it, which is called H-square statistics. In fact, it is a total variability divided by the sampling variability. So it is coming out to be 1.13. But we generally do not use this. And test for homogeneity, heterogeneity. Test for heterogeneity is Q, and it is coming out to be non-significant. But if you see the overall estimate by combining all the studies together, it is coming out to be significant. So this p-value, and this is the effect size, standard error, z value is more than 1.96, p-value is significant. So this is lower confidence interval and upper confidence interval along with p-value. So that is the entire results. And now you can also get the confidence intervals for each of these measures by giving this command, R confidence. So give the R, and you will get confidence intervals for tau square, for tau, for I-square, for this. All these confidence intervals are also here. So this is to fit a random effect model. To fit a random effect model, we have used RMA. Now, you can think of that if I want to run a fixed effect model, then I have to change this to FMA. No, it will be still RMA, but here you need to specify that your method is fixed effect, right? Method will be fixed effect. So fitting a fixed effect model, so I have used this notation meta.fe, fixed effect. And again, RMA, Y and VI, this stands for your effect size. This is your variance. Data is that one. And then method will be fixed effect. Run this command. And now you will get the results based on fixed effect. So these will be different from the other one. And here for fixed effect, you have I-square is 22 point something. And again, there is no heterogeneity. It is coming out to be non-significant. Overall effect is this one. And again, it is significant. Now, I'll discuss very important point with you, because whenever we run the mean and SD and all this, then, or with any, then there are certain plots which will appear. Forest plot we have already seen. But there are some other plots also, which you can see for consistency, which you can see for heterogeneity simultaneously. And that command is basically called plot command. It's very simple. Let's say we run plot command for RE. RE means random effect model. And you will see number of plots here. So here, if you plot, I'll show you. Let me just zoom it and explain you. First one is a forest plot. It may not be very clearly visible. We will draw it again. But all the graphs will appear. You see, it's not very clear that you can see these plots. But still, if I can able to stretch a little bit, maybe you can see these graphs very clearly. Okay. So here is a standardized mean difference, main line. Most of these studies, they are having positive effect. That means there is an effect of intervention. And these are their effect sizes and their confidence intervals. And then there is a funnel plot. Sorry, yeah, funnel plot. In funnel plot, you can see almost 4 studies on this side, 3 studies on this side, but no studies outside. Why? Because there was no heterogeneity. We have already seen with the help of with the help of Q statistics. And you know the estimated value and the actual value, then we have computed standardized residuals and they have been plotted. If standardized residual are distributed around 0, that means model is working well, right? Then this is an important plot, and it is plotted against 1 over the variance of the random effect model against Zi observation divided by the variance. And you will see this is called radial plot. Now radial plot help you to identify two things. Number one, is there any outlier or not? There is no outlier. Nothing is outside against this 95% confidence band. But you see, generally for any data, we compute mean. And what about mean? What is the interpretation of mean? That most of the observations, they are concentrated around this mean. So here, it will give you, radial plot will give you the effect size. For example, you look at this effect size, read this from the scale. So it is in between 0.67 and 0.84. Let's say it is 0.70. Suppose this point is 0.70. So I'll say that most of the studies are concentrated around the effect size of 0.70. So radial plots serve this purpose. It has two purposes. Number one, to look into the consistency, where around which point, around which effect size the observations are concentrated. Another, it can identify outlier. Is there any identify? That can also be given by funnel plot, but you can see also from the radial plot. Funnel plot doesn't give you consistency, but radial plot also give you the consistency, right? Okay, hopefully the interpretation to this is clear. So all the plots in one go you can be obtained, but they will sometimes are not very clear. And if you want to see the clear plot, then you can go for forest plot separately and zoom this. So this is a very clear forest plot, right? Overall impact is significant and all these. So very, very clear plot. Okay, so overall impact is this with confidence intervals. Summary we already have. And similarly, funnel plot you can see. This was the forest plot. This is funnel plot separately. Then another important plot to look for the outlier is, which is called quantile plot. Quantile plot is generally called QQ norm. QQ norm for random effect, and for fixed effect you can also draw. So this is a QQ plot with 95% confidence limits. And you can see this is the quantiles of normal data, and these are quantiles computed from your data. And they are within all 95% band. If they would have been outside, there was an indication of that there is some studies are having outliers. Then radial plot separately, if you want to see, you can see the radial plot separately also, right? And same plots you can draw for all these plots I have drawn for random effect. Same plots will be there for fixed effect. Just use meta fixed. The data is already there. So all the plots for fixed effect you can see, then forest plot for fixed effect, and you can, by zoom, you can see there it was around 0.63, now it is 0.61. All right. And funnel plot for fixed effect, QQ plot for fixed effect, radial plot for fixed effect, right? So here the observations are concentrated around almost the same point, maybe 0.6, 0.70. Okay. So this is all about the three data sets which we have discussed. One based on correlation, another based on binary data, where we have odds ratio, risk ratio, and we have plotted all the plots. Now we have the last data set. And before going into the last data set, let me give you a little bit of background of positive and negative cases. Why we take positive and negative cases. So let me open the PPT and show you the results from our paper. And then we will go for the actual analysis. See, AMD is called age-related macular degeneration. And there is a standard medicine which is all over the world. And that medicine is basically called Avastin. AMD is such a disease where there is a distorted vision in the center and people lose their sight. If they are having, but there are three types of AMD. One is called the wet AMD. Another is called the dry AMD. And the third one is called geographical atrophy. So there are three types of AMD. there is no treatment for wet AMD in the entire world. There is a treatment only for wet AMD, but for dry AMD, there is no treatment at all. And once people get this kind of disease, it's very difficult to handle such type of patients. And it is simply based on one medicine, which is Avastin, and sometimes people also use some dietary supplements like omega-3, etc. Right? I'm just giving you the background because before looking into the experimental picture, we should know what is happening. So age-related macular degeneration is a common degenerative disease along with the elderly population, leading to a distorted vision in the early stages and advanced stages also. AMD is a complex disease with multiple genetic and environmental factors. Analysis of data is carried out using fixed, random, and mixed effect models. The details of the studies are given in this table. So I'll show you the table also, along with the frequencies like positive, negative, control, positive, negative are mentioned here. You see, this is the data which we'll be using year from 2009 to 2011. And there are some studies in the same year also. I just haven't put the name authors, or they were complicated. So I've just written A to this 20 studies. So treatment, those who have been given treatment, but still they are having AMD is 8. Those who are not, those who have been given treatment, they don't have the AMD now is 81. Those who are having AMD is 8. This is what it means. They have been given treatment. And in control group also, they have not been given anything, but there was a control group which has been taken. And in control group also, there were some positive cases of AMD and some negative cases of AMD. And this is the entire data. This is the entire data. And weights are given for this. Weights are already given for this. So this is the entire data. And we will analyze this data using the meta-analysis. And you see, metaphor command will be used. Here is the picture of AMD. You can see that. This is optical nerve, which is on the back of our medulla, we say. It's near to retina. The blood supply, whenever there is a AMD problem, the blood supply to these veins, that stops actually. And when it stops, then particularly in wet AMD, people don't able to see anything. In dry AMD, a little bit of supply is there. People can see, but with a distorted vision, right? So this is a very complicated disease. And this is a picture of a wet AMD. This is a picture of a dry AMD. So here you can see a complete black picture of the retina. Here you can see a little bit light. Distorted vision will be there. And this is called geographical atrophy. Here nothing is visible. Okay, so these are our objectives for this data. Test the homogeneity of the existing findings. So 20 people have carried out different studies of intervention. They have given medicine to the people, and we have to see the overall effect size, then whether there is a heterogeneity present among the studies or there is a homogeneity present among the studies, then estimate the overall effect size. And we will also do the meta regression by using potential modifiers. So potential modifiers, weight will be used as modifier. Then sometimes year you can also use as modifier. And if exact age is given, you can also use that as modifier. So it varies from problem to problem. So when we use the fixed effect model, basically it is coming out to be negative because it is in terms of log actually. The entire picture is in terms of log. That's why it is coming out to be, but the effect is coming out to be significant of the, we will do it practically. And this is how the forest plot will look like for this data. It will, overall effect is coming out to be, for the relative risk is 0.90. And these are the confidence intervals. Okay. And radial plot we have already seen. You will get the radial plot for this data. This is all appeared in our paper. You can Google search and find our paper. And below each diagram, you can see the interpretation also. What is the interpretation of the radial plot? What is the interpretation of the funnel plot? So you can go through that paper. And here, the random effect model, they are again coming out to be significant at 5%. P-value is less than this. This is the p-value. Random effect results and test for heterogeneity. So all the studies were not heterogeneous, they were homogeneous. So there was a homogeneity in this paper which we have. These are the values of delta R square, delta R under root of this if you take IR square and this. So IR square determines the amount of overall variability in the effect sizes estimates attributed to the heterogeneity among the two, right? So heterogeneity, then with confidence intervals, all this is here. And this is for the random effect model. So overall, there it was 0.90, it is 0.888 because it is homogeneous data, so hardly any difference between fixed and random effect. So both models you can report. Then funnel plot, if you look at the funnel plot, now here is some problem here. Two studies it says that these are outside. That means there is some publication bias may be there. Some publication bias may be there, which you have to look into, right? And these two studies are basically outliers from the funnel plot. And this is the consistency, about the consistency, and they are consistent about this point, minus 0.13 for random effect model. This radial plots valid only for random effect model. Do not draw it for fixed effect model. This is a normal quantile plot. You can see these are the two studies where funnel plot has depicted one study this one and one study this one, which is slightly going beyond the, all the points are closer here, all studies are here, but these 2 points, first one, second one, or maybe last one. This is the second one and this is the last one. Okay. Now the results of meta regression. So we have taken two moderators now here. I'll show you practically, don't worry, because we have 10-15 minutes. I'll show you practically that one of the moderator we have taken as weight, another moderator we have taken as year, and then check its effect using meta regression. And using fixed effect model, using mixed effect model, if you see the p-value is coming out to be non-significant for weight, but it is significant for year. It is significant for year, right? And these are their estimates. And here is the Q value for moderator is coming out to, overall moderator is coming out to be significant, and residual heterogeneity is coming out to be non-significant. Then it tests the coefficient beta 1 is equal to 0. So since out of year moderator is coming out to be significant and other moderator weight is coming out to be non-significant, so beta 1 was 0, it has been ruled out. While beta 2 is 0 is there because there is a effect of moderator, right? So these are similar statistics. So this is for funnel plot for mixed effect model. This is KOQ plot for mixed effect model. And here is the conclusion, right? So I'll now go for the practical demo. I have given you the basic idea and I'll show you the practical demo, how to conduct this analysis. So I will be using that data only of 20 observations. Okay. So read the data first of all. So this is data. I've just put this data into X. So this is here. Head X means you have extracted all the variable names along with this. So first of all, estimates based on risk ratio. So here you have to specify that your AI is treatment positive, BI is treatment negative, CI is control positive, DI is control negative, data is your X, and append is equal to true. Because we have attached the data, whether you use append is equal to true doesn't matter. So first of all, based on risk ratio, what is the result? So you can see the result, and the output has been obtained. So here is, first of all, you see, this is the effect size, yi, and this is the variances that have been obtained. Now from 3 to 6, you just have the data. You remove this, just we have done earlier also. And then there are 20 studies if you want to check. K is the length of the authors, so it must be 20, so it is 20. Then fitting random effect model. Same way you can do it, which we have done earlier now. That was based on mean and SD, but it is based on positive and negative. But you are getting the same thing, YI and VI. So random effect model, RMA, random effect. Data is your DAT. So fitting this random effect. And if you want to check the results, you can. This is what I have shown you in the graphics also. and the estimates which we have shown there. So it has been practically analyzed. This paper have been published actually. So we are getting the same results, similar results, right? So this is the value of I square. The variability is 18.5% because the more or less the studies are homogeneous. They are not heterogeneous. And this is the overall effect size. But please remember, this overall effect size is in terms of log. But we have to convert this to the actual effect. So we have used the conversion now. So this is the confidence interval for different parameters. These are the confidence intervals and results for fixed effect. These are the results of fixed effect. All the results, again, there is no component of heterogeneity. All this is coming out to be non-significant. Then if you go for the plot, you will get all the radial plots, forest plot in one command. Then forest plot for random effect, you can zoom and see. This is for this, but it is for log odds ratio. It's written log odds, log risk ratio, right? But we have to get the actual value. So actual value is by using transformation. How to obtain transformation is given in the next command. This is for funnel plot for fixed effect, QQ plot, radial plot, and now we come to forest plot for random effect model. And now you see, we don't know what is happening actually. We have to write down author's name here. We have to write down that these are the events, positive events, negative, then in experimental group, in control group. So we have to beautify this actually. Now it is giving in terms of risk ratio. You see, we have made the conversion actually. Where the conversion has been made so that you can get the actual effect. Here is the conversion. First of all, you see this is specifying the character expression. Font we have used to, and AMD positive, AMD negative for control and experimental group. It is written treatment control. So all these things you can capture from here. And then relative risk, confidence intervals at particular position. So I'll run all these commands in one go. And you will see same plot with titles. You can see. Zoom this and you have a nice picture. Authors along with years, AMD positive, AMD negative in treatment group, in control group, and then the each effect size which have been computed. These are actually your YIs. And then based on VIs, variances have been computed, and you will get all the relative risk and the overall, right? So, and finally, for fixed effect, same thing, plot. So all the plots for fixed effect, and then this is for fixed effect model, funnel plot, again showing two outside, QQ plot, then radial plot for consistency, and then forest plot using author's name and combining something. All right. So you have used all these positions. So then from here to here, run all these commands together so that you can write the heading very, very clearly. From here to here. Run this and you will see for risk ratio. Right. This is fixed effect model. Earlier that was 0.88 for random effect model, and hardly any difference because heterogeneity is not there, but some question on outliers, which is marginal. So for now, the last part, you see, I have used two moderator here, and that is given by meta regression. And we have two values. One is the effect size, another is the variance. These are the two moderators. One moderator is year, another is weight, and data is given in that, right? So use these two moderators and see the effect of moderators and see the result which we have already reported. And it says the mixed effect model, 20 studies. If you are using moderators, then This is a heterogeneity combination, no heterogeneity. But if you see the moderator, QM stands for moderator, test for moderator. It is coming out to be significant. So overall test is coming out to be significant. That means there is a, if it simply says there is a effect of moderator, but I don't know whether it is a effect of moderator of weight or year. To see whether it is a effect of year, mod, or both of them, this is the command, moderator plus year, just like we do in linear regression, right? So if you run this command, you will get which one is significant, which one is not, or both of them are significant. So if you run this and again get the result, and you will see this is for weight, p-value is coming out to be non-significant. So weight doesn't play the role of moderator. What about year? P-value is coming out to be significant. So it is playing the role of a moderator, right? And you can also make future predictions. Let's say I want to give weights 10 to 16 and increase by 10 and want to make a prediction because this data is available up to 2019. Then if you give this type of weights to different studies, right, then what will be the 2015 scenario? And transformation, I'm using exponential. You are coming back to, instead of negative value, it will convert to positive value because you are taking exponential of the log, right? So this is give for the prediction. And here are the predictions. So all predicted values are, these are the predicted values for 2015, right? Odds ratio. And then go for this one. So for all the, okay, although it is not required much in detail, let me see if there is a, yeah, these are the different funnel plots which you can draw for mixed random mixed effect model, right? So they will be based on YI in this, give your data and specify the model in this format, right? Because they will be given in terms of results. So we don't require generally this type of information. So this is all about the fixed effect, random effect, and mixed effect models and meta regression. Now I'll stop the session here. Just 5-6 minutes are left, and that will be for question answer. If you have any questions, query, you can ask me, please. Yes, please. Any questions? Any question? Yes, please. Any question in chat box or somewhere?
No. Please ask your question in chat box.
You can unmute and ask, please. You can unmute and ask. Yes, please.
Sir, I think so. You have covered very well. There is no scope. You have not left any scope to ask us any question as such. It's a clear cut story, very well narrated. So, only the thing is that what will be requiring. Acha, sir, there is a question. Is there any provision for missing observations?
Yes, there is. And I'll show you that these are the studies which we have conducted on missing data also. These are papers you can refer to. These are papers by Professor Kanchan Jain, Savita Jain, and myself. And some of these papers also cover the aspect of missing values. So, because it's not possible to cover this, for example, this paper, tri-weight meta-analysis of diagnostic study using various link functions, accounting for prevalence and missing subjects. This paper, if you even put the title, you will get this. It is being published. Because when I made this slide that time, I think it was under process. It was about to publish. I didn't put in which journal, but you can search out. Just give the name. So there is a provision for missing values also, which we have given in one of the paper. And here is, you see, effect size. Sorry, the meta regression. In meta regression, you can include BMI as your moderator. You can include cholesterol as moderator. Gender can also be included. And these are all packages. As I mentioned that if you are using our libraries, then we have meta for meta-analysis. Okay, I think I have written 2 times. Okay, this is metaphor for meta-analysis and meta-regression. This is only for meta-analysis. Other packages, the CMA, as I mentioned, comprehensive meta-analysis. Then there is a review manager. A review manager is one of them. It's a free software. Meta Essentials by Rotterdam University, University of Rotterdam. This is also free. JMovie is also free. Then there are add-ons in Excel, Meta Easy and Meta Excel, right? And JMovie also. So you can, all these softwares can be used. And in my book also, I have written 1 chapter on meta-analysis, and this book is on medical statistics. There is 1 chapter on meta-analysis where all these things have been, and these are some of the references you can go through. People have done a lot of work on meta-analysis, right? These are some of the main references. Okay. Any question?
Yes, sir.
Should I stop sharing?
Sir, there are questions.
Yes.
Yes, I'm reading them out.
Hmm.
Here, I think so. There is a Satya has asked, calculate these tablets using MATLAB or some other software. I think so. Right now, you have given that idea.
Yes.
Yeah.
MATLAB, I don't know. I have never done a work. I have done a lot of work in MATLAB, but as far as meta-analysis is concerned, I think there is a statistical toolbar in MATLAB. If you go through the statistical toolbar in MATLAB, then there must be an option to do the meta-analysis. I'm sure.
Sir, one more question from Sonia is there. Can we perform meta-analysis for different sample size with different level of significance value?
For different sample sizes, you can always do. It is not necessary to
But
have the same
along
sample.
with the different level of significance, because one study maybe the sample size is 50, 29, and maybe level of significance is 5%, 10%, 2%. Like
Right.
that, if it is there, can we take them
Okay.
under the
Now,
case of different sample size only?
very good question. Very good question. Let me answer this question. Let's say some people have taken a 5% level, some person has taken a 10% level, some has taken 1% level. It may happen in different studies, right? So if you go through the book by Bornsteins, what it says actually, that you take the minimum of all levels. If you take the minimum of all levels, then you can conduct your meta-analysis in a better way. So if somebody has taken 1%, 5%, you take minimum is 1%, you take minimum as 1% and then carry out your meta-analysis. This is what generally people do. Yes, please. Any other question?
One more question is there. What is the difference between meta regression and mixed effect model by Dr. Singh? I think so. You know him. He has asked the question difference between meta regression and mixed effect model.
No, whenever we use mixed regression model, it is used
Mixed
in 2 contexts. Number 1, yeah, mixed effect model is used in 2 contexts. If there are some studies, if there are certain studies which are having fixed effect and there are certain studies which are having random effect, and you want to combine all of them together, you can use mixed effect model, right? Which I have not done here. I have not done here. And if you are doing meta regression to see the effect of moderators, again, you can use mixed effect model. That I have done here. That I use 2 moderators here and the other one weight, and shown you the effect. So there are 2 ways. One is you can perform meta analysis if there is a for mixed effect, if there is a fixed and random effect studies are there, if there are. Otherwise, for meta regression also, you have to use the same command. Command is same for both of them. Yes, please.
I think so, sir. There might be some direct question to you.
Yes, you can ask, please. Anyone can unmute and ask.
Yeah, I think so. That will be better. All of you, please unmute yourself. I think so. That option is there. Unmute yourself and ask your question.
Yes, please. Anyone? Should I stop sharing this?
Yes, sir, fine. They were one more question, common question is there, that data set link and the all your commands they want.
Yeah, I will send you this
Yeah,
file.
it
I'll
is.
send
It
you
is.
this file.
I will receive it and then I will share. I will share in the group.
Sure. I will send the data sets also. Don't worry.
I will share everything in the group. Please be there in the group. So as soon as it comes to me, I will share everything to all of
By
you.
evening, you will get it, madam.
Yes, sir.
Yeah. Any other?
Sir, one more question might be there. Just you can check if something has come directly to you. There was, I have just seen direct message.
Dr. Swarandeep Singh. Swarandeep Singh, I think, is from AIMS, All Indian Institute of Medical Science. Hopefully, he has attended the earlier workshop also. Difference between meta regression and mixed effect model. As I mentioned, in mixed effect model, it's a two-way process. If you want to perform meta regression, you can use mixed effect model, or if there are studies which are, some studies are having fixed effect, some are having random effect, still a mixed effect model can be used.
Sir, can you give this elaborate this little bit? The studies which are having random effect and
Yeah, for example, let's say there are 10 studies and three studies. Let's say I do a subgroup analysis, and for 4 studies there is a fixed effect. Let's say I mean they are very close to each other, very close to each other, and there are 4 studies, rest of the 6 studies which are slightly apart from each other, right? Now in 3 studies, in 4 studies you have a common effect, in 6 studies you don't have a common effect. So you can use, in such type of cases, the mixed effect models. In such type of studies you can use mixed. The command will be same, everything will be same, but you will see the effect of each study separately, beta 1, beta 2, for all the 10, which one is significant, which one is non-significant, it will appear.
sir, one more question is there. Sonia is asking that continuously you have used the publication bias. What do
Yes.
you exactly mean by that?
Publication bias means whenever you use the funnel plot, and if your studies are not equally distributed around mean, you have used, I have shown you the funnel plot. Let's say in one of the slide, I have shown you that if they are only on one side of the median line, on the left hand side or on the right hand side, what does this mean? That means you left out certain studies. Then in that case, publication bias will be there. And then there is a method which is called trim and fill method. And I haven't gone through trim and fill method. And if you use the trim and, but it is given in our paper. If you use the trim and fill method, it will compute the number of studies which have been left out. How? Question is how it will compute. Let's say your studies are only on the left hand side, and some of them are very close to the border of the pyramid. Let's say 4 studies are close to the pyramid border. Then it studies all the properties of those 4 studies, right? And on the right hand side, it is totally vacuum. Then it simulate that if this would have been on the right hand side, what could be the result? Then it will give you that these 4 studies, they should have been on the right hand side also. So it will simulate based on their distribution, and that is called trim and fill. And here it was the dark circle, then it will give you the circle without any dark dots in between, that these are the studies which have been left out. You must look into that. 4 studies are left out, 3 studies are left out, so approximate number will be there. That is the idea of this publication bias.
Sonia,
Yes.
hope it's a clear.
In one of the slide, I have shown you that how this, on the right hand side, there is a total vacuum. I have red circle that. So on the left hand side, if there are some studies, so it just take the negative of that, simulate that, and put it on the right hand side. So on the left hand side, it is with dark circles. On the right hand side, it is without dark circles. It will be circle only. So that you should know that these are the studies required which can complete your study. They have been left out.
Another
Funnel
question.
plot, in funnel plot, you always have a symmetry around both sides.
Another question she is asking that what is the H square?
Yeah, H square, I have given you the definition. It is residual error divided by total. Some definition was there, and it doesn't have much of the significance. It is just a measure of variation actually. But better measure is I square. Better measure is I square rather than H.
Anyone else has any question? You can unmute, either you can unmute and ask sir.
Yes, please. Any question?
Sir,
Yes.
a very simple question I'm putting. Just meta-analysis के लिए when we proceed for meta-analysis, so what should be the range of papers or we should consider? That means publication range.
Acha,
is there any criteria
no,
or
no.
guideline?
No, there is no such criteria. But only thing is, first of all, look at the funnel plot. Only criteria important is look at the funnel plot, and if in funnel plot you can see subgroupings. Let's say some studies are on the left hand side, some study their effect size on the left hand side, some on the right hand side, and some in between. Then you can it has been mentioned in the literature. It's better to go for subgroup meta type of analysis rather than combining all the studies together. Otherwise, there is no binding. You can have 50 studies, you can have 100 studies, you can have 20 studies, doesn't matter. But you at least you have more than 2.
Okay.
More than 2 is required, because otherwise other things will not be computed like mean, SD, etc. It's difficult to compute then.
Thank you, sir. And any minimum required sample size for this meta-analysis?
As I mentioned, that minimum requirement is it should be more than 2, but as far as literature is concerned, it should be 5 to 6 minimum.
Okay. Thank you, sir.
Yes. तो मैडम बताइए और कुछ, 2 बज गए.
Yes sir.
तो
Yes sir.
कहो तो एक शेर सुना दें बच्चों को.
Yes sir. Recording, you can stop the recording sir.
Yeah, please recording बंद कर दीजिए.
I was got disconnected.
Suraj, please start with the formal vote of thanks.
So, on behalf of all the participants and all my colleagues present here, I would like to thank Dr. Suresh Sharma sir for this wonderful session. As we all see, as the participants are praising sir for such a wonderful session, and we also enjoyed a lot and some new things like meta-analysis, and surely sir you have started us and you have introduced us this new concept, and surely we will work this in future. Thank you so much sir.
Thank you very much. Okay, all the best.
Thank you sir.
All right.
Thank you sir for
Leaving
sparing
the
your
meeting now.
valuable time,
Thank you, sir.
making it to be informative session.
Any participant want to say something? It's
Yes,
anything.
Yes, you can unmute yourself and
Anybody want to say something? It's up to you. Ji.
Please unmute yourself and you can express your views.
सलाम उपेंद्र.
जी सर, मैं उपेंद्र सर.
जी बोलिए.
Sir, you are always great.
No, I'm not great. You are great.
Yeah, you are great. Especially I joined in the previous program also organized by this KC.
Okay, you were there for that.
You was there for Amos, 3 days workshop on Amos.
Madam, I joined that program also. That's why sir sent me the link. Through that link, I joined this program. I'm very much interested with the talk of Mr. Sir Suresh Kumar Sharma. He is also visited our university and giving lecture on SPSS. And we have met there in the NASA during one workshop there in Delhi. Is it Delhi or Ghaziabad, sir?
No, it was in
Noida.
Noida.
Okay.
Sir, you are from which university?
Manipur University, madam.
Okay. So it's a nice
Thank
once
you.
again interacting with you.
Yeah.
Have you attended our all the sessions?
No, today's session.
Okay. Tomorrow also there will be on machine learning and AI.
Yes, sure, I will.
Yeah. It will link will be one and the same.
Yeah.
Madam, 10:30.
Hello.
Yes, sir.
Hello,
Can-
sir.
Yes, ma'am. Boliye,
Hello,
boliye.
ma'am.
Yeah.
So very good afternoon to you and all the participants and the organizers. My name is Dr. Sonia from the Maharaja Siyaji Rao University of Baroda, Vadodara, Gujarat. And this is my first association with this college, as well as, sir, I find you first time on the screen. It is really very warm session to me. एक बहुत अच्छा एकेडमिक फीस जिसको बोलते हैं वो मुझे मिला और आप नहीं मानोगे जितनी सिंप्लिसिटी से आपने एनालिसिस समझाया है आई थिंक जो फियर है लोगों में स्टैटिस्टिक्स के प्रति वो जरूर दूर होगा आई थिंक दैट इज व्हाट यू हैव मेड और आपकी शायरी तो बहुत ही अच्छी लगी that is you have cherishing the entire session with it and I'm really happy madam we need all the जितने भी स्पीकर्स आपने बुलाए हैं उनके
Yeah,
सेशंस
sure, madam.
प्लीज हमको शेयर
I have
कीजिएगा
made it.
बिकॉज इट इज डिफिकल्ट फॉर अस टू राइट एवरीथिंग
Yeah,
and
yes, madam.
we can
When you have
rewind them.
sent a request to
Yeah.
me that I cannot join the group, I have
Yeah.
immediately made it available for you because when just now you have stated your name and university, I
Yeah.
have recollected everything.
So sir
Sure,
in
madam.
सोनिया
future
मैडम आपके वहाँ पे आपके डिपार्टमेंट में प्रोफेसर मुरलीधर
yes he
प्रोफेसर
is my
श्रीवास्तव
teacher professor Rakesh Srivastava
मैं सबको
yes.
जानता हूँ सबको जानता हूँ
very well said now Vipul
say
Kalamkar
my
sir
hello to them
yeah. Sure sir I will convey your regards and it is very nice to meet you sir thank you sir
thank you anybody else otherwise फिर खत्म करते हैं thank you madam ठीक है मैडम फिर we'll leave the meeting
Yes, sir. Sure, sir.
okay all the